Welcome, space detectives. Have you ever found yourself standing beneath a sea of stars, gazing upward into that infinite, silent expanse, and felt a sudden thrill of curiosity, a deep, almost instinctual pull to uncover the hidden truths of the cosmos? There's something profoundly human about that feeling, that urge to look beyond what we know and venture into the great unknown. And tonight, we're setting out together on a journey to do just that, to shine a light on the most baffling, mind-bending mysteries our universe has to offer. From signals that defy explanation to objects that break every rule we thought governed reality, you and I are about to enter a world where science meets speculation, and wonder is always just beginning. This isn't just a list, it's an invitation to explore the very edges of human understanding, to join a global community of questioners, dreamers, and explorers united by a single shared question: what secrets is the cosmos keeping from us? Picture for a moment the sheer scale of it all. Our universe stretches across nearly 93 billion light-years, filled with galaxies, nebulae, and phenomena so strange they challenge our core beliefs about physics, time, and space itself. It's a realm where the impossible seems to happen on a daily basis, where unexplained flashes of energy streak silently through the void, and enigmatic structures drift in the darkness, almost as if they're waiting patiently for us to notice. These aren't just abstract scientific curiosities, they're cosmic stories without endings, puzzles that have captivated astronomers, ignited debates, and sometimes even kept experts awake at night, searching for answers that always seem just out of reach. Each anomaly we explore represents a frontier, an opportunity not only to marvel at the universe's creativity, but to reconnect with that childlike wonder we so often leave behind as we grow older. So settle in, open your mind, and get ready to venture into the strange and the spectacular. You're about to encounter signals from deep space with no clear origin, celestial bodies moving in ways that shouldn't be possible, and structures so enormous they redefine our understanding of the cosmos itself. This journey is more than a tour of oddities. It's a testament to humanity's endless curiosity and our relentless drive to make sense of the awe-inspiring world beyond our world. Whether you're a seasoned stargazer or someone who's simply captivated by the night sky's silent mysteries, you belong here. Together, let's unveil the top 25 unexplained space anomalies that continue to mystify, challenge, and inspire. The cosmic riddles waiting patiently for their solvers. And to truly appreciate the enigmas that await us, we must begin with one of the most famous and enduring mysteries in the history of astronomy. It all started on a seemingly ordinary night in August of 1977 at Ohio State University's Big Ear radio telescope. This massive instrument was silently listening to the cosmos, sweeping the sky and meticulously recording the faint whispers of the universe on long, continuous reams of perforated paper. The data it collected was a steady, predictable stream of cosmic background noise, a hiss of static from the vast, empty spaces between the stars. But on the night of August 15th, that quiet hum was suddenly and spectacularly interrupted. For exactly 72 seconds, the telescope's receiver was flooded with an intense, focused burst of radio waves. It was a signal so powerful and so unusual that it shot off the charts. The signal originated from a region of space in the constellation Sagittarius, near a star group known as Chi Sagittarii. What made this burst so electrifying to the astronomer, Jerry Amon, who was reviewing the data days later, was not just its strength but its precise profile. It blasted onto the printout at a frequency of 1420 megahertz, a frequency that is internationally protected, meaning no earthly broadcasts or satellites are supposed to transmit there because it's reserved exclusively for scientific research, particularly the search for extraterrestrial intelligence. It was the perfect, quiet channel for the universe to use if it wanted to be heard. The signal's intensity was recorded using an alphanumeric code, and the sequence that appeared was 6 characters long, 6 equals QUJ5. In the language of the printout, that equals sign represented a value off the scale, a signal 30 times stronger than the ambient noise of deep space. Jerry Amon, a man of science trained eye and Chinese letter restraint, was so stunned by the sheer improbability of what he was seeing that he circled the alphanumeric sequence on the printout and in the margin simply wrote one word in red pen, "Wow," and with that single human expression of awe, a legend was born. The search to explain the wow signal became one of astronomy's greatest detective stories. The immediate and most thrilling hypothesis was that this was at the moment we had finally received a deliberate transmission from an intelligent civilization light years away. The signal's narrowband characteristics were exactly what scientists predicted an artificial alien broadcast would look like. It was a perfect candidate. But science requires verification, and so astronomers pointed every instrument they could back at that same patch of sky, listening again and again for a repeat performance, for another wink from the cosmos. They listened for decades and they heard nothing, only silence. Over the years, numerous theories have been proposed to explain the signal's origin. Some suggested it was a secret military transmission, though this seems unlikely given the protected nature of the frequency. Others proposed it was a reflection of a human-made satellite signal bouncing off a piece of space debris. But the most persistent natural explanation came decades later, pointing the finger at a pair of passing comets. The idea was that the hydrogen clouds surrounding these comets could have emitted a burst of radio energy that mimicked an artificial signal. However, this theory has been heavily contested and largely debunked by many astronomers who argue the comets weren't even in the telescope's field of view at the time, and that the physics of such an emission doesn't quite fit the unique profile of the signal we observed. And so, the WOW signal remains exactly what it was on that summer night in 1977, an anomaly, a singular event. It's a one-word question written in red ink that the universe has so far refused to answer. It represents both the immense promise and the profound frustration of the search for cosmic company. It's a reminder that the universe might be sending us messages, but they could be fleeting, transient, and heartbreakingly difficult to catch. It's a mystery that continues to capture our imagination precisely because it is unresolved, a permanent beacon of possibility in the silent dark. But while signals from the cosmos tease us with the possibility of communication, some mysteries are woven into the very fabric of space itself, an unseen force holding the universe together. From the fleeting, singular event of the WOW signal, we now turn our attention to something vastly more substantial yet utterly invisible, a ghost that permeates every corner of the cosmos, dark matter. Its story begins not with a bang but with a perplexing observation. In the 1930s, a brilliant and uncompromising Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a massive group of galaxies millions of light years away. By measuring how fast these individual galaxies were orbiting the cluster's center, he could calculate the cluster's total mass, the gravitational glue holding it all together. But when he compared this gravitational mass to the mass of all the visible material, he could see the stars, the gas, the glowing dust. The numbers didn't just disagree, they were catastrophically, bewilderingly different. The gravitational force was hundreds of times stronger than what the visible matter could possibly produce. It was as if he was watching a ballet where the dancers were moving to the pull of a giant, unseen partner on the stage. Zwicky, with his characteristic boldness, proposed the existence of Dunkel Materie dark matter to account for this missing mass. At the time, his idea was so radical that it was largely dismissed by the astronomical community for decades. The case for this mysterious substance became undeniable in the 1970s with the work of astronomer Vera Rubin. She was meticulously mapping the rotation curves of spiral galaxies, charting how fast stars orbit the galactic center at different distances. According to Newtonian physics, stars on the outer edges of a galaxy, where visible matter thins out, should orbit much more slowly than those near the bright, dense center. It is a simple rule of orbital mechanics, much like how Pluto, far from the Sun, moves far more slowly than Mercury, but Rubin found something astonishing. The stars on the fringes of galaxies were orbiting just as fast as those near the center. The only conceivable explanation was that each galaxy was enveloped in an enormous, massive halo of something that wasn't emitting any light, a halo of dark matter whose gravity was whipping those outer stars around at unexpectedly high speeds. Her work proved that Zwicky's strange idea wasn't just a curiosity about distant galaxy clusters. It was a fundamental feature of every single galaxy in the universe. We now know that this enigmatic substance is not a minor component of the cosmos. It is the main event. All the stars, planets, nebulae, and every other bit of matter we can see and touch. Everything that makes up our known reality accounts for less than 5% of the total mass and energy in the universe. Dark matter makes up about 27%. It is the invisible scaffolding upon which the visible universe is built. In the early cosmos, its gravitational wells provided the necessary pull for ordinary matter to clump together, eventually forming the first galaxies and guiding the large-scale structure of the cosmic web we observe today. We can map its distribution by observing how its immense gravity bends light from distant galaxies, an effect called gravitational lensing, creating beautiful, warped arcs of light in deep space images. We know where it is, we can measure its influence with incredible precision. But after decades of the most intense scientific scrutiny, we still have no idea what it actually is. The leading hypothesis is that dark matter consists of as yet undiscovered subatomic particles known as WIMP, or weakly interacting massive particles. These hypothetical entities would not absorb, reflect, or emit light, and they would rarely interact with normal matter except through the force of gravity. For years, physicists have built incredibly sensitive detectors, often placed deep underground to shield them from cosmic rays, hoping to catch the faintest bump, the minuscule flash of heat that would signal a WIMP weakly colliding with an atom of normal matter. So far, these detectors have found nothing. Other theories propose that dark matter could be made of actions, another theoretical particle, or even that it isn't a particle at all but a manifestation of something even stranger, like parallel universes exerting gravitational influence on our own. Some scientists have even proposed that we don't need dark matter at all, and that our understanding of gravity itself is incomplete on the largest scales, a theory known as modified Newtonian dynamics, or MN. Yet most evidence continues to point to dark matter as a real, physical substance, the true identity of which remains the most significant unsolved problem in physics. It is the profound irony of our time. We are surrounded by, and indeed made possible by, a universe dominated by something we cannot see, touch, or comprehend. If dark matter is the universe's invisible skeleton, then dark energy is its mysterious breath, a force not of pull but of push, acting on the largest canvas imaginable. Our journey into this enigma begins at the close of the 20th century, a time when astronomers were confident they were on the verge of answering one of cosmology's oldest questions: what is the ultimate fate of the universe? Would the collective gravity of all matter eventually halt its expansion and pull everything back in a big crunch? Or would it simply coast onward forever, slowly fading into a cold, dark stillness? Two rival teams set out to measure this cosmic deceleration by observing distant stellar explosions. They were using Type 1, a supernova, as what astronomers call standard candles, events so uniform in their peak brightness that they act as cosmic yardsticks, allowing us to measure vast distances across the universe. By comparing how far away these supernovae were to how fast they were moving away from us, scientists could chart the expansion rate of the universe throughout its history. They fully expected to see the rate slowing down, the gravitational tug of all that matter putting a brake on the universe's growth. What they found, to their absolute astonishment, was the complete opposite. The light from the most distant supernova was far fainter than it should have been, meaning they were much farther away than predicted. The expansion of the universe wasn't slowing down at all, it was accelerating. It was as if you tossed a ball into the air, and instead of it falling back to Earth, it shot faster and faster into the sky, defying gravity itself. This discovery was so shocking and so counterintuitive that the researchers spent years double-checking their data, searching for any possible error, any hidden source of interstellar dust that could be dimming the starlight. But the result held firm. The universe was flying apart at an ever-increasing rate, driven by some unknown repulsive energy. For this revolutionary finding, team leaders Saul Perlmutter, Brian Schmidt, and Adam Rees were awarded the Nobel Prize in Physics in 2011. They had uncovered not just an answer, but a far deeper and more profound mystery. This mysterious accelerant was dubbed dark energy, and its implications are staggering. Where dark matter makes up 27% of the universe, dark energy is estimated to constitute a staggering 68%. Think about that for a moment. The entirety of the world we know, every galaxy, every star, every planet, and every one of us, is built from less than 5% of the cosmic budget. The remaining 95% is this dark, unknown sector, with dark energy as its dominant, enigmatic force. Its effect is to create a kind of negative pressure, a repulsive gravity that stretches the very fabric of spacetime itself. The most straightforward explanation, and the one currently favored by the standard model of cosmology, harkens back to an idea first proposed by Albert Einstein. He called it the cosmological constant, a fixed, inherent energy density woven into the vacuum of empty space itself. Einstein originally introduced the concept to force his equations to describe a static universe, a notion he later called his greatest blunder after Edwin Hubble discovered the universe was actually expanding. Yet, in a bizarre twist of fate, his blunder may have been prophetic. If this vacuum energy is real, it means that true, empty space is not nothing. It is a seething, bubbling foam of virtual particles popping in and out of existence, and it possesses a fundamental energy that is relentlessly pushing the universe apart. However, the cosmological constant comes with its own profound puzzle, known as the cosmological constant problem. When quantum physicists try to calculate the theoretical value of this vacuum energy, their predictions are off by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. It is arguably the worst prediction in the entire history of physics. This colossal discrepancy suggests that our understanding of the quantum vacuum and gravity on cosmic scales is severely incomplete. This has led other theorists to propose that dark energy might not be constant at all. Perhaps it is a dynamic field nicknamed quintessence after the ancient Aristotelian fifth element. Unlike a static cosmological constant, quintessence could change in strength over time, fluctuating and evolving as the universe expands. This would mean the acceleration we see today might not be a permanent feature of the cosmos. It could increase, decrease, or even reverse in the far, far future. The most radical proposition is that dark energy isn't a substance or a field, but a signpost pointing to a fundamental flaw in our understanding of gravity itself. Einstein's theory of general relativity has passed every test thrown at it for over a century, but those tests have primarily been within our solar system or in strong gravitational fields. Perhaps on the largest scales of the universe, across billions of light years, relativity breaks down and requires modification. Maybe the acceleration is an illusion caused by our particular place in an inhomogeneous universe, or a sign of extra dimensions we cannot perceive. Dark energy, therefore, is more than just a mysterious force. It is a direct challenge to our most fundamental theories of physics. It asks us to reconsider the nature of nothingness, the validity of our most successful scientific theories, and the ultimate destiny of all existence. While dark matter hints at new particles hidden in the shadows, dark energy suggests that the void itself is alive with a power we are only beginning to glimpse. Yet, even as dark energy pushes the universe apart on the grandest scale, another mysterious and opposing force is pulling on our own cosmic neighborhood with irresistible strength. Imagine you are a leaf floating on a vast, slow-moving river carried along by the current. Now, imagine you begin to notice that you and every other leaf around you are all drifting not just with the flow, but toward a specific, powerful whirlpool many miles ahead. You cannot see this vortex because a dense, impenetrable fog blankets the water in that direction, but its pull is undeniable, drawing you in with a force you cannot resist. This is the essence of our situation within the Laniakea supercluster. While our galaxy, the Milky Way, seems to be moving through space, we are in fact caught in a vast cosmic current, all of it streaming toward a single, unseen point of immense gravity, a cosmic anomaly astronomers call the Great Attractor. Our story of this mysterious pull begins closer to home with the simple observation of our own motion. We know our galaxy is not stationary. The Sun orbits the galactic center, and the Milky Way itself is on a collision course with our nearest large neighbor, the Andromeda Galaxy. But in the 1970s, astronomers mapping the large-scale flow of galaxies made a startling discovery. They found that not only is our local group of galaxies moving, but the entire system. The Milky Way, Andromeda, and all their satellite galaxies are all traveling together at an astonishing speed of over 600 kilometers per second. That is about 2.2 million kilometers per hour. We are hurling through the void at an incredible velocity, but the question was, toward what? The initial assumption was that this motion was directed toward the dense and massive Virgo cluster, the heart of our local supercluster. But further measurements revealed that the Virgo cluster's gravity was only a small part of the story. It accounted for only a fraction of the force needed to pull us at such a high speed. Something far more massive lying beyond Virgo was doing the bulk of the pulling. That something was given a name that captured both its power and its mystery, the Great Attractor. Pinpointing this gravitational beacon, however, presented an enormous challenge because of our own galaxy's obstructing bulk. To understand this, picture yourself trying to see a distant city at night, but a large, brightly lit building is directly in your line of sight. The building's glare and structure completely obscure your view of anything behind it. For astronomers trying to peer into the depths of space toward the Great Attractor, that brightly lit building is the plane of our own Milky Way. This region is known as the Zone of Avoidance. It is an area of the sky heavily obscured by thick clouds of interstellar gas and dust, as well as the dense concentration of stars in the galactic core. For centuries, this zone remained a blind spot in our maps of the universe, a blank and mysterious area on celestial charts. The Great Attractor lies directly behind this zone, in the direction of the constellation Centaurus, making it incredibly difficult to observe with traditional optical telescopes. For a long time, its true nature was shrouded in literal cosmic dust. The breakthrough in unraveling this mystery came with the development of new technologies that could see through the obscuration. Astronomers began using radio, infrared, and X-ray telescopes, instruments that can peer through the dust clouds that block visible light. What they began to see was not one single, impossibly dense object, but an immense confluence of mass. They discovered that the Great Attractor is actually the gravitational core of our home supercluster, Laniakea, a Hawaiian word meaning immeasurable heaven. This vast cosmic structure is a web of galaxies over 500 million light-years across, containing over 100,000 galaxies, all bound together by gravity. The gravitational heart of Laniakea, the point toward which we are all flowing, is a massive cluster of galaxies known as the Norma cluster. This cluster, combined with the entirety of the surrounding supercluster's mass, creates the powerful gravitational pull we experience as the Great Attractor. Yet, even with this identification, the mystery has not been entirely solved. While the mass of the Norma cluster and the Laniakea supercluster is immense, some studies suggest it might still not be quite enough to account for the full intensity of the observed pull. This has led to the proposal of an even more colossal structure lying in the same direction, far beyond the Great Attractor itself. This potential entity, known as the Vela supercluster, was only confirmed in 2016. It is a massive wall of galaxies that could be contributing additional gravitational influence, adding yet another layer of complexity to the cosmic currents that guide our journey. The Great Attractor, therefore, may not be a final destination, but merely a waypoint in a much longer voyage, a gravitational stepping stone pulling us toward structures of almost unimaginable scale hidden deep in the cosmos. It serves as a profound reminder that we are part of a dynamic, moving universe, forever caught in the gravitational tides of structures we are only just beginning to map and understand. But as we chart these immense gravitational currents that shape our cosmic neighborhood, we must also tune our ears to the universe's most fleeting and explosive symphonies, bursts of energy so powerful and so brief they defy easy explanation. From the grand, slow-motion pull of the Great Attractor, we now shift to events that unfold in the blink of an eye, fast radio bursts or FRB. Imagine if all the energy our Sun releases over an entire 80-year period was compressed into a single, brilliant millisecond and fired across the cosmos like a cosmic laser beam. That is the staggering, almost incomprehensible power of an FRB. These events are not gentle whispers from the void. They are deafening, universe-spanning shouts that arrive without warning, their origins shrouded in intense mystery. The story of their discovery begins in 2007, when astronomer Duncan Lorimer and his student David Narkevic were sifting through archived data from the Parkes radio telescope in Australia. They were looking for new pulsars, the rapidly spinning, highly magnetized corpses of dead stars that emit regular radio pulses. But buried in that old data from 2001, they found something that didn't fit any known pattern. A single, colossal burst of radio energy that lasted just 5 milliseconds. It was so bright that it saturated the telescope's receiver, and it appeared to have come from far outside our own galaxy. For a time, the astronomical community was skeptical. Could this be some kind of terrestrial interference, a glitch in the machine, or perhaps a microwave oven being opened prematurely at the observatory itself? But as years passed, more of these bursts were discovered by other telescopes around the world, confirming that FRBs were indeed real and they were coming from deep space. The mystery was genuine and the race to understand them was on. What makes FRBs so captivating to scientists is their dual nature. Some of these bursts are lone wolves, single, incredibly powerful events that flash once in the cosmic dark and are never heard from again. Others are repeaters, firing off multiple bursts from the same location in an unpredictable, staccato pattern. This dichotomy immediately suggested that there might not be one single cause, but perhaps multiple cosmic phenomena capable of producing these extraordinary flashes. The hunt was on to pinpoint their galactic addresses, and the first major breakthrough came in 2017 when a repeating FRB was finally traced back to its host galaxy. The source wasn't some exotic, distant quasar. It originated in a small, puny dwarf galaxy over 3 billion light-years away. This localization was a crucial clue, narrowing down the possible culprits capable of creating such immense energy. The most favored explanation for many FRBs involves some of the most extreme and magnetic objects in the universe, magnetars. These are a specific type of neutron star, the ultra-dense remnant of a supernova explosion, but with a magnetic field so powerful it defies comprehension. A magnetar's magnetic field is 1,000 trillion times stronger than Earth's. It's so strong that it can literally twist the star's solid crust, causing starquakes that release titanic amounts of energy in the form of gamma ray or radio flares. In 2020, a magnetar within our own Milky Way galaxy was observed producing an FRB-like burst, providing the first direct evidence that these objects are indeed capable of such powerful emissions. This was a monumental step forward, suggesting that at least some FRBs are natural cosmic catastrophes. However, the magnetar theory, while compelling, doesn't seem to explain all FRBs. Some bursts are far too energetic, and some repeating sources show patterns and behaviors that don't perfectly align with our models of magnetar activity. This has led scientists to explore other violent cosmic events. One possibility is the collision of two incredibly dense objects like neutron stars merging. The cataclysmic impact of such bodies could release a final, tremendous burst of energy as they spiral into each other. But this theory has a significant drawback. Such collisions are destructive, one-off events. They cannot explain the repeating FRBs that continue to signal from the same spot over and over again. It is this persistent, repeating nature of some FRBs that inevitably sparks the most tantalizing and speculative of all hypotheses. Could they be evidence of advanced technology? The idea, proposed seriously by some astronomers, is that an extremely advanced civilization might use powerful bursts of energy to propel enormous light sails across interstellar distances. A beam focused on a sail could push a spacecraft to a significant fraction of the speed of light, and from our distant vantage point, that fleeting beam sweeping across our telescope would appear as a brilliant milliseconds-long flash. While this is firmly in the realm of speculation and is considered a last resort explanation, the fact that it is even discussed in scientific circles highlights how truly enigmatic these signals remain. They represent a frontier where known physics meets the thrilling possibility of the unknown, a reminder that the universe is capable of generating wonders we have not yet even begun to dream of. While the universe sends us brief flashes of energy and invisible forces shape our journey, it also occasionally sends physical visitors from the depths of interstellar space. In October of 2017, astronomers at the University of Hawaii's Pan-STARRS telescope spotted something extraordinary. It was a faint point of light moving swiftly against the backdrop of stars, and its trajectory was unlike anything seen before. This was not an object from our own solar system lazily orbiting our sun. This was an intruder, a traveler from the vast expanse between the stars. They named it Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. It was the first confirmed interstellar object ever detected passing through our cosmic neighborhood, and it was far stranger than anyone could have predicted. As astronomers around the world trained their telescopes on this mysterious visitor, its peculiarities began to mount. The first and most obvious oddity was its shape. By carefully measuring how its brightness changed as it tumbled through space, scientists deduced that Oumuamua was not a roughly spherical object like most asteroids or comets. Instead, it was dramatically elongated, shaped like a pancake or a cigar, with estimates suggesting it was up to 10 times longer than it was wide. This was an utterly bizarre form for a natural space rock, as most objects are rounded by collisions and gravitational forces over time. Its surface was also unusually reflective, with a reddish hue that suggested a metallic or carbon-rich composition, having been baked by cosmic rays during its epic journey across the galaxy. It was a shape more commonly associated with science fiction than with observational astronomy. But the true mystery, the detail that truly set the scientific world alight, was its motion. As Oumuamua sped away from the sun, it began to accelerate in a way that could not be explained by gravity alone. When a typical comet swings around the sun, its ices heat up and vaporize, creating a visible atmosphere called a coma and a tail of dust and gas. This outgassing acts like a natural rocket engine, giving the comet a slight non-gravitational push. Oumuamua, however, showed no visible coma or tail. Not a single speck of dust or puff of gas was detected around it, yet something was clearly pushing it, providing a precise and steady acceleration as it departed. It was as if an invisible force was propelling it on its way. This anomaly forced astronomers to confront a truly puzzling question. What mechanism could possibly cause this acceleration without any of the telltale signs we associate with cometary activity? The scientific community scrambled to find natural explanations. One theory proposed that Oumuamua could be a hydrogen iceberg. In the coldest depths of interstellar space, molecular hydrogen could theoretically freeze solid. As this block of frozen hydrogen neared the Sun, it would sublimate transition directly from a solid to a gas, providing the necessary thrust without creating a visible dusty coma. The problem with this elegant idea is that a hydrogen iceberg is incredibly fragile. It likely would not have survived the long journey through interstellar space, let its close passage by our star. Other scientists suggested it might be a rare type of extremely porous, low-density dust aggregate, like a cosmic dust bunny, whose lightweight nature could allow radiation pressure from the Sun to push it. However, the math on this rarely works out for an object of Oumuamua's inferred size. Perhaps the most compelling natural explanation is that Oumuamua is a fragment from a shredded planet. In young solar systems, planets are formed through violent collisions, and these impacts can sometimes shatter worlds, ejecting shards of rock into the void. A shard from a Pluto-like body, for example, could be rich in nitrogen ice. As nitrogen ice sublimates near the Sun, it could provide the observed push while leaving behind very little visible dust, potentially explaining the lack of a coma. This theory has gained some traction, but it remains difficult to prove definitively for an object that is now long gone, speeding out of our solar system and beyond the reach of our telescopes. It was this combination of highly unusual characteristics, the strange shape, the mysterious non-gravitational acceleration, and the complete absence of any visible outgassing, that led renowned Harvard astronomer Avi Loeb to propose a more speculative hypothesis. Could Oumuamua be a piece of advanced alien technology? Loeb suggested that the object's flat, pancake-like shape and its precise acceleration profile were consistent with a light sail, a form of propulsion that uses radiation pressure for thrust. It could be a derelict probe, a functional piece of equipment, or even a discarded artifact from a distant civilization, now drifting silently among the stars. While this idea was met with significant skepticism from much of the scientific community, who emphasized the importance of exhausting natural explanations first, it captured the public imagination and sparked a vital conversation about how we interpret anomalies. Oumuamua, in the end, serves as a profound and humbling reminder. The universe is capable of creating objects and phenomena that defy our immediate understanding. It challenges our assumptions and forces us to broaden our perspectives, proving that sometimes the most exciting discoveries are the ones we cannot easily explain. While our solar system was visited by a single, enigmatic traveler in Oumuamua, another mystery was brewing around a distant star, one that would capture the world's imagination and ignite a debate that continues to this very day. Its official designation is a jumble of letters and numbers, KIC 8462852, but the world knows it as Tabby's star, named after the astronomer who led its investigation, Tabitha Boyajian. It earned another name too, one born from internet speculation and a sense of cosmic wonder, the alien megastructure star. Nestled in the constellation Cygnus, about 1,400 light-years from Earth, this seemingly ordinary star became the center of one of the most captivating astronomical detective stories of the 21st century, all because of its bizarre and unprecedented flicker. The story begins with the Kepler Space Telescope, a revolutionary mission designed to find planets beyond our solar system by staring unblinkingly at a single patch of sky, monitoring the brightness of over 150,000 stars. Its method was simple but powerful. It looked for the telltale, periodic dips in a star's light that occur when an orbiting planet crosses in front of it. These transits are usually small, predictable, and rhythmic, like a perfectly timed clock. But the data from this particular star was anything but normal. Citizen scientists, part of the Planet Hunters project, were the first to flag the strange light curve, and what they found was so unusual that it defied all conventional explanation. Instead of the neat, symmetrical dips caused by planets, this star's light was plunging in erratic, chaotic, and dramatic ways. The dimming events were staggering in their depth and irregularity. Planets, even gas giants the size of Jupiter, block at most about 1% of a star's light. The dips from Tabby's star were profound, with one event showing a breathtaking 22% drop in brightness. That's not a small shadow, it's the equivalent of something colossal passing in front of the star, blocking nearly a quarter of its light. Furthermore, these dips didn't follow a regular schedule. They would occur at random intervals, last for wildly different durations, sometimes days, sometimes weeks, and exhibit strange, asymmetrical shapes. It was as if the star was being obscured by a vast, uneven, and constantly shifting swarm of objects, a celestial swarm of bees darting unpredictably in front of a cosmic lantern. The scientific community immediately began searching for a natural culprit, and the first and most favored theory involved a massive family of comets. The idea was that a giant cloud of cometary fragments, perhaps disturbed by the gravity of a passing star, could be circling Tabby's star in a highly elliptical orbit. As these icy bodies neared their star, they would vaporize, creating enormous clouds of dust and debris that could account for the irregular, deep dimming. This was a solid, plausible hypothesis grounded in known physics, but it soon began to show cracks. Follow-up observations, particularly in the infrared, revealed a problem. A vast cloud of dust, like that proposed in the comet swarm model, should heat up as it absorbs the star's light and re-radiate that energy as infrared warmth. Yet when astronomers pointed the Spitzer Space Telescope at Tabby's star, they found a puzzling lack of excess infrared radiation. The dimming was happening, but the telltale heat signature of the obscuring dust was mysteriously absent. It was this frustrating lack of a clear natural explanation that opened the door to a far more speculative, yet utterly fascinating idea. In a 2015 paper, astronomers Jason Wright and Stein Sigurdsson floated a possibility that instantly captured the public's imagination. Could the dimming be caused by a megastructure? Specifically, they suggested the signature could be consistent with a partially constructed Dyson sphere, a hypothetical concept proposed by physicist Freeman Dyson in the 1960s. The theory posits that a highly advanced civilization, having exhausted the energy resources of its home planet, might eventually build a vast array of energy-collecting satellites or panels encircling its star to harness its entire power output. Such a colossal, incomplete structure with panels and struts orbiting in irregular formations would block light in exactly the erratic, deep, and non-periodic way we observed. The lack of excess infrared would also make sense, as an advanced civilization would presumably be capturing that stellar energy for its use, not wastefully radiating it away as heat. While the megastructure hypothesis was always considered a last resort explanation, its sheer audacity transformed Tabby's star from an obscure astronomical anomaly into a global phenomenon. It sparked a massive citizen science-funded Kickstarter campaign that raised over $100,000 to secure dedicated telescope time for further monitoring. This unprecedented public involvement led to the detection of another series of major dimming events in 2017, providing a wealth of new data. These subsequent observations have strongly pointed back toward dust as the primary culprit, but a very peculiar kind of dust. The dimming was more pronounced in blue light than in red light, which is a classic signature of fine dust particles scattering light. much like our own sky appears blue because tiny molecules scatter blue light more effectively. This suggests the occluding material is not solid, opaque megastructure components, but rather a mysterious, uneven cloud of microscopic particles. So where does that leave us? The comet swarm theory persists, though it requires a truly immense number of comets to explain the deepest dips. Other proposals include the aftermath of a catastrophic planetary collision that littered the system with debris, or perhaps the ongoing disintegration of a giant planet whose remains are spiraling into the star. Yet, even with dust seeming to be the leading actor, fundamental questions remain stubbornly unanswered. What is the source of this immense, ever-changing dust cloud? What mechanism could create and sustain such a dynamic, colossal structure around a star, and why do we not see similar phenomena elsewhere? Tabby's star stands as a powerful testament to a simple truth. Sometimes the universe presents us with a puzzle so complex that it forces us to question our assumptions and consider possibilities at the very edge of imagination. It reminds us that the line between natural wonder and the signature of intelligence can be tantalizingly blurry, and that the pursuit of an answer is often just as thrilling as the answer itself. Just when we thought we were beginning to understand the rules of the cosmos, the universe presented us with a galaxy that seemed to break them all. For decades, the story of galaxy formation seemed to have a clear, consistent protagonist: dark matter. This invisible substance, as we explored earlier, is the gravitational anchor for every galaxy we've ever studied, the essential scaffolding upon which stars collect and spiral galaxies take shape. It is the universe's hidden architect, and its presence was considered non-negotiable. That is, until astronomers discovered a galaxy that appeared to be built from nothing but the stuff we can see. A galaxy that, against all expectations, seemed to have no dark matter at all. Its name is NGC 1052 DF2, and its very existence became a profound cosmic paradox. The discovery of this celestial rebel was made by a team led by astronomer Pieter van Dokkum at Yale University, using a unique telescope called the Dragonfly Telephoto Array. This instrument isn't a typical giant mirror. It's an array of commercially available telephoto lenses specially modified to be exquisitely sensitive to extremely faint diffuse light. Its purpose is to find a specific, elusive class of objects, ultra-diffuse galaxies. These are galaxies as large as the Milky Way, but with only a tiny fraction of its stars, making them incredibly dim and ghostly. In 2018, while studying such galaxies in the vicinity of the massive elliptical galaxy NGC 1052, Van Dokkum's team found something that didn't just look unusual, it behaved unusually. To measure the amount of dark matter in a galaxy, astronomers don't look for the dark matter itself. They measure its gravitational influence on the things they can see. The team turned their attention to 10 bright globular clusters, dense, spherical swarms of stars that orbit the galaxy's center. By carefully tracking the velocities of these clusters, they could calculate the total mass of the galaxy pulling on them. The results were staggering. The mass calculated from the motion of the clusters was almost exactly equal to the mass of all the visible stars and gas within the galaxy. There was no extra mass, no hidden gravitational source. The dark matter, which should have made up over 90% of the galaxy's mass, was simply missing. This was like weighing a sealed box, hearing rocks rattling around inside, but finding the box's weight matches the weight of the rocks alone, with no room for the box itself. The finding was so counter to established theory that the initial reaction within the astronomy community was one of intense skepticism. Could there be a mistake in the distance measurement? If the galaxy were much closer to us than assumed, its stars would be intrinsically dimmer, and the calculated mass would be wrong. The team meticulously checked and rechecked the distance, using multiple independent methods, and consistently found that NGC 1052 DF2 is indeed about 65 million light-years away, confirming the initial bizarre result. The immediate question was, how could such a galaxy even form? Our standard model of cosmology, known as the lambda cold dark matter model, posits that galaxies are born within halos of dark matter. Without this gravitational well, ordinary gas would not have clumped together densely enough to trigger the star formation that builds a galaxy. The existence of a galaxy like NGC 1052 DF2 poses a direct challenge to this foundational idea. It suggests that there might be previously unknown pathways for galaxy formation, routes that don't require the dominant presence of dark matter. One compelling theory is that this galaxy was born from a very different kind of cosmic event. In the dense, chaotic environment of a galaxy group, vast streams of gas can be pulled out during violent interactions between large galaxies. If this stripped gas later coalesces and forms stars, it could create a galaxy that essentially forms within a pre-existing void of dark matter, inheriting the motion of its parent galaxies rather than being anchored by its own dark matter halo. This would make it a sort of cosmic orphan, a galaxy born from the debris of a larger collision rather than from its own primordial cloud of dark matter. However, the plot thickened just a few years later with the discovery of another similar galaxy, NGC 1052 DF4. This galaxy also showed a startling lack of dark matter, and it was located in the same region of space. This wasn't just a single, freak occurrence. It suggested a small population of these oddballs might exist, pointing to a specific, repeatable process in that particular galactic neighborhood. The presence of the massive galaxy NGC 1052 nearby is a crucial clue, hinting that its powerful gravitational influence might be responsible for creating these dark matter-deficient anomalies through a process called tidal stripping. Yet, even this explanation faces challenges, as the process is difficult to model, and some studies suggest the galaxies might not be close enough to NGC 1052 to have undergone such an extreme transformation. The discovery of these galaxies has forced a healthy and necessary scientific debate, one that revolves around two equally fascinating possibilities. The first is that our methods are correct and these galaxies truly are devoid of dark matter, which would force us to revise our models of galaxy formation and acknowledge that the universe has more than one way to build an island of stars. The second possibility is that our understanding of dark matter itself might need refinement. Perhaps dark matter can interact with itself or with normal matter in ways we haven't yet accounted for, making it appear absent in certain configurations. Or perhaps the laws of gravity themselves operate differently on the scale of galaxies than we think, a proposition known as modified Newtonian dynamics or MND. Interestingly, the existence of galaxies without dark matter is actually a problem for MND, which was invented to explain galactic rotation without invoking dark matter. MND predicts that a galaxy's visible mass should always account for its dynamics, so finding a galaxy that perfectly follows this prediction, like NGC 1052 DF2, should be a triumph for MND. But the catch is that MND also struggles to explain the behavior of every other galaxy we see, which clearly do require extra mass. This leaves scientists in a fascinating bind, where no single theory perfectly explains the full spectrum of observations. Ultimately, NGC 1052 DF2 is more than just an oddity. It is a critical test case. It doesn't necessarily invalidate the existence of dark matter. In fact, most physicists remain confident dark matter is real, but it does challenge our assumptions about its universality and its role in the birth of every single galaxy. It proves that the cosmos is a laboratory of immense diversity, capable of producing outcomes we didn't predict and forcing us to look harder, think deeper, and remain open to the possibility that for every rule we establish, the universe might have an exception waiting to be found. After exploring galaxies that defy our understanding of matter and stars that flicker with no clear cause, we arrive at perhaps the grandest and most humbling mystery of all. one that doesn't involve a single object or signal, but the overwhelming, echoing silence of the cosmos itself. This is the Fermi Paradox, a concept that strikes at the very heart of our place in the universe. It's the startling contradiction between the incredibly high probability that extraterrestrial civilizations should exist and the complete and utter lack of any evidence that they do. The paradox gets its name from a casual lunchtime conversation in the summer of 1950. Physicist Enrico Fermi, while discussing flying saucer reports with colleagues, reportedly blurted out a simple, profound question that has resonated ever since: but where is everybody? His point was grounded in straightforward logic. Consider the numbers. Our Milky Way galaxy alone contains an estimated 100 to 400 billion stars. Many of these stars are billions of years older than our Sun, and a significant percentage are likely orbited by planets in the habitable zone, the so-called Goldilocks region where conditions might be right for life. Even if the chance of intelligent life emerging on any given planet is infinitesimally small, the sheer scale of the universe, with its trillions upon trillions of stars across 2 trillion galaxies, makes it seem almost statistically inevitable that life should be common. Furthermore, given the age of the galaxy, any civilization that arose just a few million years before us would have had more than enough time to develop interstellar travel and colonize vast swaths of the Milky Way. The galaxy should be teeming with life, buzzing with activity. Our skies, in theory, should be filled with the traffic of cosmic empires, and yet we hear nothing. We see nothing. We are surrounded by a silence that is, as author Milan Cirkovic put it, deafening. This glaring absence of evidence has spawned a vast array of potential explanations, each more mind-bending than the last. One of the most compelling and unsettling ideas is the Great Filter hypothesis. This theory suggests that there exists some incredibly difficult step, some nearly insurmountable barrier, in the evolutionary chain from non-life to a spacefaring civilization. This filter acts as a galactic bottleneck, wiping out almost all life before it can achieve interstellar communication or travel. The terrifying question for humanity is where this filter lies. Is it behind us, perhaps the emergence of life itself, or the jump from simple prokaryotic cells to complex eukaryotic cells is so astronomically rare that it has only happened once in our galaxy? If so, we are impossibly, miraculously alone. Or, even more chillingly, is the great filter ahead of us? Perhaps every advanced civilization eventually discovers some technology, whether it be nuclear war, engineered pandemics, or runaway artificial intelligence, that inevitably leads to its own destruction. In this scenario, the eerie silence of the cosmos is a cemetery quiet, a warning of a fate that may still await us. Other explanations are less apocalyptic but no less strange. Perhaps we are looking for signs of life all wrong. Our search for extraterrestrial intelligence, or SETI, primarily listens for radio waves, a technology we developed in the 20th century. But a civilization just a few thousand years more advanced than us might have moved far beyond such primitive communication methods, using something we can't even conceive of, like neutrino messaging or quantum entanglement. We might be like islanders trying to spot smoke signals while the rest of the world is communicating by satellite phone. Alternatively, space travel might be far more difficult and costly than we imagine, making galactic empires impractical. The mind-boggling distances between stars, the hazards of cosmic radiation, and the sheer energy required could simply imprison every civilization in its own solar system, leaving us all as isolated islands in a vast ocean, aware of each other's potential existence but forever separated. Then there are the sociological and philosophical possibilities. Maybe advanced civilizations are out there, but they have no interest in expansion or communication. They could be in a state of technological singularity, having merged with their machines and existing in a virtual reality, utterly indifferent to the physical universe outside. Or perhaps they are observing us but following a strict policy of non-interference, a galactic prime directive, choosing to let us develop on our own without influence. Another haunting idea is that we are, in fact, early to the party. The universe may now be habitable, but for most of its 13.8 billion-year history, it was a violent, inhospitable place, filled with gamma-ray bursts and frequent supernova that sterilized planets. We might be among the first generation of civilizations capable of looking up and asking these questions. Each of these answers offers a different vision of our future and our cosmic significance. The Fermi Paradox forces us to confront our deepest hopes and fears. It is the ultimate exercise in humility, reminding us that our data set of intelligent life currently contains exactly one example, us. We are left staring into the silent darkness, forced to wonder if we are a cosmic miracle, a cosmic tragedy waiting to happen, or simply one voice in a chorus we haven't yet learned how to hear. The silence is not an empty void. It is a canvas onto which we project our greatest questions about life, intelligence, and our own lonely, curious place in the grand scheme of things. Yet as we ponder the profound silence of the cosmos, we are reminded that some of the most enduring mysteries are much closer to home, waiting for us right in our own celestial backyard. Our very own moon, that familiar companion in the night sky, holds a secret that has left planetary scientists utterly baffled for decades. We've walked on its surface, brought back hundreds of pounds of its rock, and mapped its terrain in exquisite detail. And yet, one of its most fundamental ancient characteristics defies every conventional explanation. The mystery revolves around something we can't even see, a magnetic field. Today, the moon is a largely inert, unmagnetized rock, but analysis of the Apollo mission samples tells a completely different story for its distant past. Those ancient lunar rocks, some over 4 billion years old, bear the unmistakable imprint of having been forged within a powerful magnetic field, one that was likely even stronger than Earth's is right now. This presents a colossal puzzle, one that strikes at the heart of planetary science. Magnetic fields are generated by what's known as a dynamo effect, the churning movement of electrically conductive material within a planet's core. For a dynamo to work, you need a fluid core, a source of energy to keep it moving, and a sufficiently fast rotation to organize that motion. Earth has all of these things. Our planet's rapid 24-hour spin and its large molten iron core, kept hot by the radioactive decay of elements like potassium and thorium, power a magnetic field that protects our atmosphere and guides migrating birds. The moon, by contrast, seems to be a terrible candidate for such a phenomenon. It is small, with a correspondingly small core. It rotates slowly, completing a turn only once every 27 days. And it should have cooled down incredibly quickly after its formation, its internal fires snuffed out by its relatively tiny size. By all rights, the moon's dynamo should have been weak, short-lived, or never existed at all. The fact that it was not only present but also remarkably powerful for over 1 billion years is a paradox that demands a radical solution. Scientists have proposed several compelling theories to solve this conundrum, each more dramatic than the last. One leading hypothesis points to the moon's very origin story. The prevailing giant impact theory suggests the moon was formed from the debris ejected when a Mars-sized protoplanet, often called Theia, slammed into the early Earth. This cataclysmic birth would have left the newborn moon incredibly hot, perhaps with its interior structure arranged in a unique way that supercharged an early dynamo. Another fascinating idea suggests the moon's rotation could have been significantly faster billions of years ago. The gravitational tug of war with Earth through tides has gradually slowed the moon's spin to its current sluggish rate. A faster spinning young moon could have provided the necessary mechanical energy to stir its core and sustain a magnetic dynamo for much longer than its current rotation would allow. Perhaps the most imaginative theory involves a massive, later impact. The Moon's surface is a testament to a violent past, scarred with enormous impact basins. The event that created the Imbrium Basin, one of the largest craters in the solar system, was an impact of almost unimaginable force. Some researchers propose that such a colossal collision could have delivered a gigantic energy punch to the Moon's interior, literally shocking its core back to life. This impact-induced stirring could have reignited a dormant dynamo, causing a temporary but powerful resurgence of the magnetic field that was then captured in the rocks formed during that era. It's a concept that paints a dynamic picture of a moon whose internal engine was jump-started by external catastrophe. Yet, for all these creative theories, the lunar magnetic field remains an enigma. Each proposed solution has its own set of challenges. The energy from a fast-spinning early moon might not have been sufficient. The heat from a giant impact would have faded relatively quickly. Reconciling the timing and duration of the field's strength with any single event has proven to be exceptionally difficult. This mystery forces us to reconsider the basic principles of how planetary interiors work. It suggests that small bodies can generate powerful fields through mechanisms we haven't fully discovered or understood, which has profound implications for our search for life on distant exoplanets and moons. If a small, rocky world like our moon could once have had a protective magnetic shield, then perhaps many more celestial bodies could have as well, increasing the potential habitats for life in the universe. The moon, our constant and seemingly familiar neighbor, continues to guard ancient secrets, reminding us that sometimes the greatest mysteries are not found in the depths of space, but are lying right at our feet, waiting in the rocks we brought home. While we grapple with mysteries locked within our own solar system, the universe continually sends us messengers of unimaginable power from the farthest reaches of deep space. These are cosmic rays, not rays of light but atomic fragments, protons and atomic nuclei traveling at nearly the speed of light. They constantly pepper our planet, but most are low-energy particles born from our sun or from within the Milky Way. The real enigma, the ones that truly confound physicists, are the ultra-high-energy cosmic rays. These are the outliers, the extreme athletes of the particle world, carrying energies so immense they defy belief. To put it in perspective, the most powerful particle accelerator ever built by humans, the Large Hadron Collider, can propel a single proton to an energy of about 13 tera-electronvolts. Now, imagine a single subatomic particle, a lone proton, arriving from deep space with an energy exceeding 320 exa-electronvolts. That's millions of times more powerful than anything we can create on Earth, carrying the kinetic energy of a well-thrown baseball, all compressed into a single, tiny particle. It is an absolutely staggering amount of energy for something so small, and the question of what natural particle accelerator in the cosmos could possibly achieve this is one of the most profound puzzles in astrophysics. The journey of these particles is a saga of epic proportions. They travel for millions, sometimes billions, of light years across the vast, mostly empty voids of intergalactic space. But this journey is not a straight shot. Space is not a perfect vacuum. It is filled with the sparse photons of the cosmic microwave background radiation, the faint afterglow of the Big Bang. As an ultra-high-energy proton travels, it inevitably collides with these background photons. According to the laws of physics, such a collision should sap the proton's energy over long distances. This creates a theoretical limit known as the GZK cutoff, beyond which we should not be able to detect protons from very far away because they would have lost all their energy bumping into these photons along the way. The fact that we continue to detect particles with energies far beyond this limit means one of two incredible things. Either these particles are coming from relatively nearby sources within our own galactic neighborhood, which is problematic because we don't know of any local objects capable of such power, or our understanding of particle physics across cosmological distances is fundamental. Incomplete, it's a classic cosmic catch-22 that lies at the heart of the mystery. So what cosmic engines could possibly be capable of such feats? Astronomers have several prime suspects, each more violent and extreme than the last. The leading candidates are active galactic nuclei, the incredibly luminous hearts of some galaxies, powered by supermassive black holes that are actively feeding on surrounding matter. As vast disks of gas and dust spiral into these gravitational monsters, intense magnetic fields and friction heat the material to millions of degrees, while powerful jets of plasma are often shot out from the poles at relativistic speeds. It is within these chaotic, magnetized jets that particles could potentially be accelerated to the phenomenal energies we observe. Another formidable candidate is the gamma-ray burst, the most explosively energetic events in the universe since the Big Bang itself. Born from the collapse of massive stars or the mergers of ultra-dense neutron stars, these blasts unleash more energy in a few seconds than our Sun will in its entire 10 billion-year lifespan. The shockwaves from such apocalyptic events could easily serve as the ultimate particle accelerators, firing off bullets of atomic matter across the cosmos. Yet, despite these compelling theories, pinning down the exact source has proven to be maddeningly difficult. The first major challenge is that cosmic rays are not like light, they are charged particles. This means that as they travel through space, their paths are bent and twisted by the magnetic fields that permeate our galaxy and the space between galaxies. By the time one of these particles slams into the upper atmosphere over Earth, creating a vast shower of secondary particles that we can detect, it is impossible to simply trace its trajectory back in a straight line to its point of origin. It's like trying to find the source of a river when you're only given a single wayward raindrop that has bounced off 1,000 leaves on its way down. The second challenge is their incredible rarity. The highest energy cosmic rays are exceptionally rare, striking a given area the size of a football field only about once per century. Catching them requires enormous, sophisticated detectors. This is where instruments like the Pierre Auger Observatory in Argentina come into play. It is not a traditional telescope but a colossal array of over 1,600 water tanks spread across 3,000 square kilometers of desert, an area larger than Rhode Island. These tanks detect the faint flashes of light produced when a cosmic ray's atmospheric shower particles travel through the water. By combining data from this vast network, scientists can estimate the energy, direction, and type of the primary particle. Even with this incredible setup, the results have been tantalizing but inconclusive. Data from the Auger Observatory has shown a weak correlation between the arrival directions of the highest energy cosmic rays and the locations of active galaxies with ferociously feeding black holes. It's a compelling hint, a statistical whisper pointing a finger toward these celestial powerhouses, but it is not yet a definitive conviction. The evidence isn't strong enough to rule out other sources or to explain the precise acceleration mechanism at work. The mystery of ultra-high-energy cosmic rays is a humbling reminder of the raw, untamed power of the universe. It underscores the limits of our current technology and understanding, showing us that nature possesses particle accelerators that dwarf our greatest engineering achievements. Each rare detection is a message from the most violent and energetic corners of creation, a clue written in a code we are still learning to decipher, pointing toward processes that push the very laws of physics to their breaking point. For decades, the twin probes Pioneer 10 and Pioneer 11 were celebrated as intrepid explorers, the first human-made objects to venture beyond the asteroid belt, the first to visit Jupiter and Saturn, and the first to set a course that would eventually carry them out of our solar system entirely. They were marvels of engineering, carrying with them the now famous golden plaques designed to describe humanity to any extraterrestrial intelligence that might one day find them. But as they sailed ever farther into the black, dutifully phoning home their data across billions of miles, the scientists monitoring their journey began to notice something peculiar. A tiny, persistent anomaly was hiding in the data, a ghost in the machine that would puzzle physicists for years. It started as an almost imperceptible nagging in the Doppler shift of their radio signals. As the pioneers hurtled toward the outer solar system, the frequency of their signals, caused by the motion between the spacecraft and Earth, was being minutely distorted by an unexplained force. The effect was incredibly small, an acceleration of about 8.74 times 10 to the negative 10 meters per second squared. To put that in human terms, it's equivalent to the gravitational pull you'd feel if you were standing on Earth and gained just 1/10,000,000th of your weight. It was a minuscule amount, but over the vast distances and timescales involved, this tiny, unaccounted-for push was enough to throw the probes about 400,000 kilometers off their predicted courses, a distance greater than that between the Earth and the Moon. And most baffling of all, this mysterious force was not random. It was a constant sunward deceleration, as if an invisible tether was ever so gently pulling the spacecraft back toward our star. Naturally, such a precise and consistent anomaly sent ripples of excitement through the scientific community. Could this be the first hint of a flaw in Einstein's theory of general relativity? Was it evidence of some new, unknown force in the universe, or perhaps the gravitational influence of dark matter clustered around our solar system? The most tantalizing possibility was that it pointed toward a modification of gravity itself, a new physics that operated on large scales, challenging Newton's inverse square law. For a time, the pioneer anomaly became one of the most discussed puzzles in fundamental physics, a potential key to unlocking secrets about the very fabric of reality. The painstaking search for an answer became a decades-long forensic investigation. A dedicated team of scientists led by Slava Turyshev embarked on a monumental effort to recover old telemetry data stored on outdated magnetic tapes and decades-old computer formats. They pieced together the entire history of the probe's journeys, modeling every conceivable physical effect with exquisite detail. And slowly, a more mundane culprit emerged from the data: heat. The Pioneer spacecraft were powered by radioisotope thermoelectric generators, which produced heat as a byproduct of generating electricity. This heat radiated away from the spacecraft in all directions. However, the craft's design was asymmetrical. Equipment boxes and the main antenna created surfaces that absorbed and re-radiated this heat unevenly. The team built a sophisticated thermal model and discovered that a tiny, non-uniform net recoil force from this thermal radiation was being exerted on the spacecraft. Because the antenna was pointed back toward the Sun and Earth, this force acted as a very slight brake, creating the appearance of a sunward pull. When this thermal model was applied, it accounted for the vast majority of the anomalous acceleration. With this discovery, the case was largely considered closed by the mainstream scientific community. The grand mysteries of new physics faded, replaced by a story of incredible engineering precision and the subtle, often overlooked, effects of thermal management in the vacuum of space. It was a triumph of meticulous scientific detective work, demonstrating that even the tiniest of effects must be accounted for when operating at the limits of measurement. Yet for some, a sliver of the mystery endures. While the thermal radiation explanation accounts for most of the anomaly, a very small residual effect, a tiny fraction of the original signal, stubbornly remains unaccounted for. It's a whisper in the data, so faint it could easily be an unmodeled systematic error, a final ghost in the machine we haven't exercised. This lingering uncertainty is a powerful lesson in itself. It reminds us that our understanding of the universe is built on a foundation of constant questioning and re-examination. The Pioneer anomaly, even in its resolution, stands as a testament to the importance of precision, the need to chase down every clue no matter how small, and the humbling reality that sometimes the universe's greatest secrets are hidden not in the grand gestures but in the subtle, quiet details. Yet as our robotic envoys journeyed silently toward the stars, another probe was already circling a distant world, capturing images of a mystery so geometrically perfect it seemed almost artificial. When the Voyager spacecraft flew past Saturn in the early 1980s, it revealed many of the ringed planet's splendors for the first time. But one discovery tucked away at the North Pole was so bizarre that it left scientists scratching their heads. There, dominating the atmospheric canvas, was a massive, stunningly precise hexagon. This wasn't a feature carved into the planet's surface, but a colossal jet stream, a six-sided wall of wind racing around the pole, with each side longer than the diameter of Earth. It was a shape you'd expect to see in a crystal or a honeycomb, not churning within the turbulent, storm-ridden atmosphere of a gas giant. Even more astonishing when the Cassini spacecraft arrived over 2 decades later to conduct a long-term study of Saturn. This enormous geometric wonder was still there, unchanged, a permanent feature etched into the planet's weather for at least 40 years and likely much longer. How could such an orderly, angular structure form and persist in a chaotic fluid environment where random, swirling storms are the norm? The search for an answer has largely moved from the cosmos to the laboratory, where physicists use creative simulations to unravel the secrets of fluid dynamics. The leading theory suggests the hexagon is a type of standing wave, a stable pattern that emerges from the complex interplay between the deep, churning currents inside Saturn and its rapid rotation. Saturn is the fastest spinning planet in our solar system, completing a full rotation in just about 10.5 hours. This fierce rotation creates powerful Coriolis forces, which deflect moving air into curved paths, much like how it creates spiraling weather systems on Earth. In laboratory experiments, researchers have placed a small ring inside a cylinder of fluid and spun it rapidly. When the ring rotates at a different speed than the cylinder, the shear between these layers can generate stable polygonal shapes in the fluid, including squares, octagons, and yes, hexagons. This suggests that deep beneath Saturn's cloud tops, different atmospheric layers might be moving at different velocities, shearing against each other and giving rise to this colossal, stable wave pattern pinned firmly to the planet's north pole. But a simple lab analogy can only take us so far. Saturn's atmosphere is not a vat of water in a controlled experiment. It's a deep, chaotic, and immensely powerful system of hydrogen and helium whipped by supersonic winds and colossal storms. The hexagon's sheer scale and longevity present challenges that our current models struggle to fully replicate. Why a hexagon? Why not a pentagon or a heptagon? The specific geometry might be dictated by the precise speed differentials and viscosities within Saturn's internal weather patterns, a delicate balance of forces that we have not yet been able to measure directly. Furthermore, the hexagon is not a static drawing. It is a dynamic river of wind. Within its boundaries, the jet stream screams along at speeds exceeding 320 kilometers per hour, and the entire structure rotates with a period of about 10 hours and 39 minutes, which intriguingly might be linked to the rotation period of Saturn's deep interior itself. Adding another layer to the mystery is the fact that nothing like it exists at Saturn's south pole, which instead features a more conventional, though still massive, hurricane-like vortex. This asymmetry tells us that the conditions needed to create and sustain the hexagon are incredibly specific. Some researchers have proposed that the hexagon might be a towering structure, a wave that extends hundreds of kilometers vertically down into the planet's atmosphere, its roots anchored in deep weather systems we cannot see. The Cassini spacecraft provided some support for this, finding that the hexagon extends much higher up into the atmosphere than previously thought, creating a kind of towering wall of air. Yet, even with this wealth of data, a complete predictive model that can perfectly account for its formation, its precise shape, and its staggering endurance remains just out of reach. It stands as a breathtaking example of how nature can produce order from chaos, a gravitational and fluid dynamic masterpiece that we can observe from 1 billion miles away but have yet to fully comprehend from our laboratories here on Earth. But if Saturn's hexagon is a masterpiece of natural order, the cosmos also creates structures of breathtaking fragility that defy our expectations of stability. Journey far beyond our solar system into the deep black between galaxy clusters, and you'll find a class of objects so ethereal they seem to be made of ghostly cobwebs stretched across the void. These are the ultra-diffuse galaxies, and their existence presents a paradox that quietly upends our assumptions about how galaxies live and die. Imagine a city as vast as New York, but with only a handful of streetlights scattered randomly across its boroughs. The overall structure is there, the potential is immense, but it remains almost completely dark, a skeletal outline waiting for a population that never arrived. This is the essence of an ultra-diffuse galaxy. They possess the sheer physical size of a grand spiral like our Milky Way, spanning tens of thousands of light years, yet they contain only about 1% of its stars. They are cosmic will-o'-the-wisps, vast and sprawling yet so faint that they blur the very line between a galaxy and the empty space surrounding it. The mystery of their formation is a two-part puzzle beginning with their birth. How does a cloud of gas manage to sprawl out to such an enormous size without condensing down to form a dense, star-filled core like most other galaxies? The prevailing theory points to a turbulent and high-energy youth. In the early universe, galaxies were not the isolated islands we often imagine. They were constantly jostling, merging, and interacting in a violent cosmic dance. One compelling idea is that many ultra-diffuse galaxies are failed galaxies. They may have begun their lives with normal amounts of gas, but they formed in relatively empty cosmic deserts, regions devoid of the dense flows of intergalactic gas that typically fuel sustained star formation. Without this external fuel source, their star-making machinery simply sputtered and died early on, leaving behind a massive but barren structure. Another, more dramatic origin story involves galactic collisions. When two large galaxies graze each other in a near miss, immense tidal forces can pull and stretch them, literally shredding stars and gas into vast streaming arcs. Some of this material, now spread incredibly thin, may never recoalesce, instead becoming a new, diffuse galaxy all its own, born from the violence of its parents. Their existence, however, is only half the enigma. The second, and perhaps more profound, question is one of survival. How does something so large and so faint not simply fly apart? According to our standard models of physics, a structure with so little visible mass should not have enough gravity to hold itself together against the internal motions of its own stars. It should have dissolved back into the intergalactic medium billions of years ago. And even if it could hold itself together, how has it avoided being completely torn to shreds by the gravitational tides of any larger, neighboring galaxies it might encounter? This is where the dark matter hypothesis becomes absolutely critical. For most ultra-diffuse galaxies, the answer seems to be that they are, in fact, not lightweight at all. They are overwhelmingly massive, but nearly all of that mass is locked away in enormous, dominant halos of dark matter. Their faintness is an illusion. They are sleeping giants, their incredible gravitational bulk hidden in a form we cannot see, which perfectly binds their sparse stars into a stable, lasting structure. Yet, as with so many cosmic rules, there appears to be a spectacular exception. The discovery of galaxies like NGC 1052DF2, which we discussed earlier, threw this neat explanation into disarray. These galaxies appear to have no dark matter at all, yet they still maintain their ultra-diffuse form. This shocking finding suggests that the category of ultra-diffuse galaxies might be far more diverse than we imagined, with multiple formation pathways. Some are dark matter-dominated fortresses, while others might be fragile, dark matter-free ghosts that have somehow managed to persist through sheer luck. perhaps by orbiting in particularly quiet corners of the universe where disruptive gravitational forces are minimal. Their continued existence challenges us to consider whether our understanding of gravity itself needs refinement on these vast scales, or if we are witnessing the signature of previously unknown physical processes that can stabilize matter without the glue of dark matter. These faint, sprawling giants are more than just astronomical curiosities. They are natural laboratories, testing our most fundamental ideas about the invisible forces that sculpt the universe and govern the life cycle of galaxies. And now we arrive at a cosmic mystery so profound that its very name suggests a challenge to our fundamental understanding of the universe. It's called the axis of evil, and it isn't some apocalyptic prophecy, but a chillingly precise alignment found in the oldest light we can see. This story begins with the afterglow of creation itself, the cosmic microwave background radiation. This faint, cold whisper of energy is the cooled remnant of the Big Bang, a snapshot of the universe when it was just 380,000 years old, a hot, dense plasma that finally cooled enough for light to travel freely across space. For decades, this cosmic background has been the bedrock of modern cosmology, and its near uniformity has powerfully supported the cosmological principle. This is the foundational assumption that, on the largest scales, the universe is homogeneous and isotropic. It looks the same in every direction and has no special place or center. It is the ultimate declaration of cosmic democracy, insisting that our view from Earth is in no way privileged or unique. This is why the first detailed all-sky map of this radiation, produced by NASA, a Wilkinson Microwave Anisotropy Probe, or WMAP, was expected to show a beautiful, random distribution of tiny temperature fluctuations. These tiny ripples, hotter and colder spots representing the seeds of future galaxies, were indeed found. But as cosmologists delved deeper into the data, they began to uncover something unsettling. The fluctuations weren't entirely random. They appeared to be aligned along a specific axis that stretches through our solar system, a preferred direction in the cosmos that seems to point toward the constellations Leo and Virgo. This alignment was so statistically unexpected, so seemingly orchestrated, that it was dubbed the axis of evil, a name reflecting how deeply it contradicts our standard model of the universe. If the universe is truly isotropic, such a pronounced and coherent directional preference should not exist. It's as if you walked into a vast, supposedly random forest and found that a majority of the tallest trees were all leaning in precisely the same direction. The implications of this are staggering. A preferred axis suggests the universe might have a structure or a drift on the largest possible scale, a fundamental lopsidedness that would dethrone the cosmological principle and force a complete rewrite of our textbooks. It could imply that our universe is not the same in all directions after all, that it has a discernible fabric or flow, or even that it was shaped by forces existing before the Big Bang itself. Some of the most mind-bending theories proposed to explain it involve our universe colliding with another universe in the multiverse, an event that could have imprinted a directional bias on our cosmic infancy. Others suggest it could be evidence that the universe is actually rotating on a grand scale, a concept that itself challenges Einstein's theory of general relativity. Naturally, the scientific community has responded with intense scrutiny, and the leading explanation remains the most mundane. It could all be a colossal statistical fluke. When you're analyzing a massive dataset, even random noise can sometimes create patterns that appear significant. Alternatively, the anomaly might not be in the cosmos but in our own backyard. Could it be contamination from within our solar system? Perhaps the gravitational influence of nearby structures is subtly lensing the ancient light, creating a false signal. Or, most embarrassingly, could it be an unaccounted-for systematic error in the instruments themselves, a subtle bias in how the satellites collected their data that was mistakenly interpreted as a cosmic feature? The subsequent Planck satellite, which mapped the cosmic microwave background with even greater sensitivity, also found hints of this anomalous alignment, though some of its features were less pronounced. This both strengthened the case for its existence and fueled further debate. The axis of evil, therefore, remains in a state of scientific limbo. It is a persistent whisper of something wrong, a crack in the foundation of cosmology that is too significant to ignore yet not definitive enough to force a paradigm shift. It represents the thrilling, frustrating, and essential process of science at its frontier. It is the uncomfortable data point that keeps cosmologists awake at night, a haunting reminder that our most cherished principles are always provisional, always subject to revision by the next great discovery from the depths of space and time. And from the grand, unsettling possibility of a cosmic axis that challenges our view of the entire universe, we now turn our gaze to a single, breathtakingly beautiful galaxy that defies our understanding of how such structures are built. This is Hoag's object, a celestial marvel so perfect it looks less like a natural formation and more like a piece of divine geometry painted onto the black canvas of space. Discovered by astronomer Art Hoag in 1950, it presents us with a mesmerizing puzzle. A brilliant, near-symmetrical ring of young, hot, blue stars encircles a much older yellow core of stellar seniors. These two distinct populations are sharply separated by a vast, seemingly empty gap of darkness, creating a perfect cosmic bullseye floating in the void. The sheer beauty of this structure is matched only by the depth of the mystery it presents, forcing us to ask how such a perfectly balanced dual-system galaxy could have possibly come to be. The most intuitive explanation for a ring galaxy is a violent and dramatic one, a galactic collision. We've seen this story before. The Cartwheel Galaxy, for instance, is a classic example of a so-called bull's-eye ring galaxy, and its structure is clearly the result of a smaller galaxy piercing the center of a larger disk galaxy like a bullet. The gravitational shockwave from that catastrophic impact sends a rippling wave of density and pressure racing outward through the galactic disk, compressing interstellar gas and triggering a firestorm of new star formation in a perfect ring. This is a well-understood process, but Hoag's object refuses to fit neatly into this narrative. Detailed observations have failed to find any evidence of a second galaxy, any shred of debris or telltale gravitational distortion that would point to a recent collision. The core is perfectly intact, serene, and undisturbed, sitting placidly at the center of its brilliant blue halo. It shows no signs of the violent trauma that would be necessary to create its ring through such an impact. This galaxy appears to have formed its perfect ring in isolation, a feat that current astrophysical models struggle to explain. Without the convenient culprit of a collision, astronomers have had to venture into more subtle and complex theories. One compelling idea involves the delicate and powerful forces of resonant dynamics. In this scenario, a natural instability or a minor perturbation within the original disk galaxy could have created a standing density wave, a stable, non-moving ripple in the fabric of the galaxy itself. This wave would act like a cosmic traffic jam, herding stars and gas into a specific circular orbit. As this gas piles up at the resonance point, it becomes dense enough to collapse under its own gravity, igniting the spectacular burst of star formation that we see as the luminous blue ring. The old stars in the core would remain relatively unaffected, locked in their own orbits, while the new ring of stars establishes itself at this precise galactic radius. It's a theory of majestic, slow-motion self-organization, a galactic rhythm that gives rise to order without any external catastrophe. Another hypothesis suggests a much slower, more gradual process called accretion. Perhaps a smaller, gas-rich dwarf galaxy ventured too close to Hoag's object billions of years ago. Instead of a direct disruptive collision, this neighbor could have been gently torn apart by tidal forces, its stolen gas slowly siphoned off and captured by the larger galaxy's gravity. This captured material, now swirling in a vast ring around the host's core, could have then condensed to form the new stars we see today. This would be a quieter, more graceful form of galactic cannibalism, one that leaves the central core untouched while building a new stellar city in the suburbs. Yet, even this theory has its challenges, as it typically predicts a less perfectly symmetrical ring and some residual evidence of the disrupted donor galaxy, evidence that remains elusive. What makes Hoag's object even more fascinating is that it is not entirely alone. A deeper look into the gap between its core and ring reveals a faint smudge of light, another, much more distant ring galaxy, perfectly aligned in our line of sight. This incredible coincidence serves as a reminder of both the rarity and the potential prevalence of such structures across the universe. Hoag's object stands as a sublime counterpoint to the chaotic, collision-driven models of galaxy formation. It suggests that under the right conditions, galaxies can achieve a state of serene, symmetrical equilibrium, becoming cosmic mandalas whose very existence hints at the beautiful and hidden laws of dynamics that govern the evolution of our universe. It is a quiet, persistent enigma, a reminder that not all cosmic wonders are born from violence. Some are formed through a delicate and still mysterious dance. Amidst the grand, sweeping mysteries of dark energy and galactic structures, a more intimate and peculiar enigma has captured the public imagination for decades, one that supposedly orbits just a few hundred miles above our heads. It's a tale that intertwines early space-age history, misunderstood science, and the enduring human desire to find evidence that we are not alone. This is the legend of the Black Knight satellite, a story that begins not with a clear image or definitive detection, but with a series of intriguing, disconnected events that were later woven together into a compelling, if unfounded, narrative. The modern myth paints a picture of an ancient, alien artifact, a silent, foreign probe in a near-polar orbit around Earth, supposedly thousands of years old, watching and waiting. Its origins are often traced back to enigmatic radio signals and fuzzy photographs, creating a tapestry of evidence that, when examined individually, unravels into a series of mundane explanations. The first thread in this tapestry dates back to the very dawn of the space race. In 1954, just a few years before Sputnik, newspapers including the St. Louis Post-Dispatch and the San Francisco Examiner ran stories citing a statement by UFO researcher Donald Keyhoe. He claimed that the U.S. Air Force had reported two objects orbiting Earth, objects that were not man-made. These reports were likely based on early, misinterpreted tracking of secret military satellite tests or even natural phenomena, but they planted a powerful idea in the public consciousness. Something unknown was already up there. The legend gained its most enduring fuel a few years later, in 1961. A French magazine called Aviation Magazine published an interview with a man named Jacques Vallée. Vallée, who would later become a renowned astronomer and ufologist, mentioned a mysterious, dark object in a polar orbit. This detail was seized upon by enthusiasts, but the crucial context was often left out. Vallée was almost certainly referring to a very real and very secret American satellite discovery. At the time, the U.S. was launching covert spy satellites, and the Soviets were doing the same. It was an era of orbital secrecy, and discovering the other side's hardware was a key intelligence goal. The dark object was far more likely a classified Soviet satellite than an alien one, but the mystery was too tantalizing to dismiss. Then came the signals. Perhaps the most convincing piece of the puzzle for many was the story of the long-delayed echo. In the 1920s, a pioneering Norwegian engineer named Georgian Howells was experimenting with radio waves, bouncing signals off the ionosphere. He sometimes heard his own signal echo back a few seconds later, a phenomenon that baffled scientists of the day. Decades later, these strange echoes were retroactively linked to the Black Knight myth, proposed as evidence of an alien object reflecting our transmissions. However, physicists have since offered several natural explanations, suggesting the echoes were likely caused by complex radio wave propagation in the upper atmosphere, a newly discovered and not yet understood effect at the time, rather than a solid object in space. The myth reached its visual apex with the space shuttle. In 1998, the crew of the Space Shuttle Endeavour on mission STS-88 photographed a strange, dark object during their flight to the nascent International Space Station. The images show a vaguely irregular, flat object against the curvature of the Earth. These photos swiftly became the smoking gun for Black Knight believers, presented as definitive proof of the anomalous satellite. In reality, the object was quickly identified by NASA as a thermal blanket. The crew had lost it during an earlier spacewalk. It was a piece of their own equipment drifting aimlessly away from them. It was human-made space debris, a common and unfortunately growing feature of the orbital environment, not an ancient alien observer. So why does the story persist with such vigor when every piece of evidence has a prosaic explanation? The answer lies in the powerful allure of the idea itself. The notion of a silent sentinel, a watchful eye from another star system that has been circling our world since before the pyramids were built, taps into a deep-seated part of our psyche. It's a narrative that is far more romantic and thrilling than the reality of discarded insulation and misidentified spy satellites. The Black Knight is a classic modern legend, a cultural artifact born from a combination of Cold War paranoia, the excitement of the space age, and our timeless fascination with the possibility of extraterrestrial visitors. It serves as a perfect case study in how myths are constructed in the information age, where disparate facts can be linked by narrative rather than evidence, creating a story that is, in the end, much more compelling than the truth. In the grand cosmic ballet of stellar life and death, we often imagine a star's final act as definitive, a spectacular, all-or-nothing explosion that leaves behind either a ghostly nebula or an ultra-dense corpse. But the universe, it seems, has a flair for the bizarre and the incomplete, a fact perfectly illustrated by one of the most peculiar stellar phenomena ever discovered, the Type IX supernova. Imagine a bomb that only partially detonates, a firework that fizzles after the first spark. This is the essence of a Type IX event, a stellar explosion that somehow fails to finish the job, leaving behind a bruised, battered, but still burning remnant, a star that quite literally comes back from the dead. Astronomers have fittingly nicknamed these survivors zombie stars, and their very existence forces us to rewrite the textbook on how stars die. To understand why this is so strange, we first need to look at the standard stellar explosion it so eerily mimics, the Type Ia supernova. This well-understood cataclysm is one of the most important events in cosmology. It involves a white dwarf, the Earth-sized, super-dense core of a dead, sun-like star. This white dwarf resides in a binary system, and it's a cosmic vampire, relentlessly siphoning material from its companion star. Over time, it gorges itself, adding more and more mass. There is a critical threshold, a point of no return known as the Chandrasekhar limit, which is about 1.4 times the mass of our Sun. Once the white dwarf reaches this limit, the immense pressure and heat at its core trigger a runaway nuclear fusion reaction. This fusion rips through the entire star in a matter of seconds, unleashing an energy so titanic that the white dwarf is completely and utterly annihilated. It's a total, unstoppable thermonuclear detonation that leaves absolutely nothing behind but an expanding cloud of hot, newly forged elements like iron and silicon. It's this consistent, predictable brightness that makes Type Ia supernova such perfect standard candles for measuring the vast distances of the universe. Now picture that same scenario, but with a crucial malfunction. The vampire white dwarf begins to feed, it approaches the Chandrasekhar limit, and the nuclear inferno ignites. But this time, the flame doesn't race through the star with the same devastating efficiency. It sputters, it fizzles, the explosion is weaker, slower, and asymmetrical. Instead of being completely vaporized, the white dwarf is violently disrupted. A huge portion of its mass is blown out into space in a still impressive blast, but a chunk of the star's core manages to survive the ordeal. This leftover piece is the zombie star. It's sent reeling away from the blast site at incredible speed, a shrapnel fragment of its former self, bruised and battered but still glowing from the residual heat of the aborted explosion. This is the Type IX supernova, a partial explosion, a failed Type Ia, a cosmic whimper that stands in stark contrast to the definitive bang. The existence of these zombie stars raises two profound and deeply puzzling questions. First, how does the explosion fail? What physical mechanism causes the fusion flame to be so much weaker and less efficient? One compelling theory points the finger at the composition of the white dwarf itself. Perhaps in these systems, the material being siphoned from the companion star is helium-rich rather than carbon-rich. Helium fusion is notoriously more volatile and unstable than carbon fusion. It's possible that the helium on the outer layers of the white dwarf ignites first, creating a shockwave that prematurely triggers the carbon fusion in the core before the star is perfectly primed. This out-of-sync detonation could lead to a weaker, pulsating explosion that doesn't have the energy to fully unbind the entire star. It's like trying to light a damp log. It might catch fire and burn for a while, but it won't combust completely in a single brilliant flash. The second, even stranger question is, what does the zombie star remnant actually look like? After surviving such a traumatic event, it is fundamentally altered. It's no longer a stable white dwarf. Observations suggest these remnants are grotesquely distorted objects. They are much larger and puffier than a typical white dwarf, glowing not from new fusion but from the immense heat of the explosion that almost destroyed them. They are in essence a hot, exposed stellar core, blasting out intense ultraviolet radiation as it slowly cools over thousands of years. Some models even suggest that the explosion could leave behind a bizarre object known as a white dwarf pulsar, a rapidly spinning remnant with an incredibly powerful magnetic field. The zombie star is a completely new class of stellar object, a previously unknown phase of stellar evolution that we are only just beginning to catalog and understand. The discovery of Type IX supernova is a humbling reminder that nature rarely follows our cleanest theoretical models. It shows us that even the most violent and seemingly definitive processes in the universe can have exceptions, failures, and strange variations. These zombie stars are the exceptions that prove a much more interesting rule, that stellar death, like stellar life, exists on a spectrum. They challenge us to refine our simulations, to question our assumptions, and to keep our eyes peeled for other cosmic anomalies that whisper secrets about the messy, unpredictable, and utterly fascinating physics that governs the lives and deaths of stars. Far beyond the orbit of Neptune, in the cold, dark reaches of our solar system, lies a vast and mysterious frontier known as the Kuiper Belt. This distant realm is home to a diverse population of icy bodies, remnants from the solar system's earliest days, including the beloved dwarf planet Pluto. For decades, astronomers have mapped this region, expecting its population to gradually thin out the farther one travels from the Sun, much like a cosmic beach where the sand slowly gives way to the ocean. But recent surveys have revealed something deeply puzzling, a boundary so abrupt and unexpected it has been dubbed the Kuiper Cliff. At approximately 50 astronomical units from the Sun, that's 50 times the distance from Earth to the Sun, the number of detected Kuiper Belt objects doesn't gently decline, it plummets. It's as if you were walking along that beach and suddenly, without warning, stepped off the edge of a continental shelf into an abyssal plain. This sharp drop-off presents a direct challenge to our most fundamental models of solar system formation, which predict a much more gradual decrease in object density. The cliff suggests something is actively shepherding this distant frontier, and the most thrilling possibility is that we are feeling the gravitational influence of a world we have yet to lay eyes on. This is where the hunt for Planet 9 enters the story. The idea of a large, unseen planet lurking in the outer darkness is not new. It's how we discovered Neptune itself by tracking its gravitational pull on Uranus. The modern hypothesis for Planet 9 was propelled by a different set of orbital oddities. Astronomers Konstantin Batygin and Mike Brown at Caltech noticed that the most distant Kuiper belt objects, those with highly elongated orbits that take them hundreds of astronomical units from the Sun, share a peculiar characteristic. Their orbits are clustered together, and their points of closest approach to the Sun, their perihelia, are grouped in a similar direction of space. For this clustering to persist and not be randomized over billions of years by the gravity of the giant planets we know, the models suggest it must be shepherded by the persistent tug of a massive object. Their calculations point to a world with a mass roughly 5 to 10 times that of Earth, on a colossal elliptical orbit that takes it between 300 and 1,000 astronomical units from the Sun. A single orbit for this proposed planet could take an astonishing 10 to 20,000 years. The gravitational influence of such a body could very well be the sculpting force behind the Kuiper Cliff, efficiently ejecting objects from that region or herding them into orbits that keep them away from the cliff's edge, effectively creating a gravitationally carved void. However, the Planet 9 theory, while compelling, is not the only possible explanation for this distant anomaly. Some planetary scientists argue that the cliff might not point to a present-day planet, but could instead be a fossilized relic from the solar system's violent infancy. Our current model of planetary formation, the NICE model, describes a period of dramatic instability among the giant planets shortly after they formed. During this chaotic era, Jupiter, Saturn, Uranus, and Neptune likely migrated from their original orbits, scattering countless icy planetesimals in every direction. This grand reshuffling could have stripped the outer disk of material very early on, depositing it into the scattered disk or ejecting it from the solar system entirely, and leaving behind a sharp edge that has been frozen in time for billions of years. In this scenario, the Kuiper Cliff is not a dynamic feature being maintained today, but a ghostly imprint of a cataclysm that occurred over 4 billion years ago. The orbital clustering of extreme objects could then be explained as a similar fossilized effect, a memory of a past gravitational disturbance rather than an ongoing one. The search for a definitive answer is a monumental technical challenge. Surveying the sky for a faint, slow-moving object at such incredible distances requires the most powerful telescopes and immense patience. Projects like the Vera-C, Rubin Observatory's legacy survey of space and time are poised to revolutionize this search. With its ability to scan the entire visible sky deeply every few nights, it could either finally catch a glimpse of Planet 9's faint glow or, perhaps just as importantly, rule out its existence across vast swaths of its predicted orbital path. Each new discovery of an extreme trans-Neptunian object adds another data point, refining the possible location of the hypothetical planet or further testing the limits of the fossilized relic theory. The Kuiper Cliff stands as a stark reminder that our solar system story is far from fully written. It represents a boundary not just in space, but in our understanding, a tantalizing puzzle that pushes our observational capabilities to their limit and forces us to consider whether we share our celestial neighborhood with a giant world still waiting to be discovered. But while we search for phantom planets in our own solar system, cosmologists have been grappling with a missing persons case of cosmic proportions, one that involves the very stuff we're made of. You see, we've spent a lot of time talking about dark matter and dark energy, the mysterious components that make up 95% of the universe. But what about the remaining 5%? This is the ordinary matter, the baryonic matter, that constitutes everything we can see and touch, every star, every planet, every human being. It's the atoms forged in the hearts of stars and the cataclysmic explosions of supernova. And for decades, we've had a pretty good idea of how much of this regular matter should exist, based on precise measurements of the cosmic microwave background, the afterglow of the Big Bang. That primordial fingerprint tells us exactly how much ordinary matter the universe started with. The problem is when astronomers add up all the visible matter they can find in the modern universe, all the stars, the glowing gas in galaxies, the dust, they come up dramatically short. They can only account for about half of what should be there. It's as if you carefully counted all the supplies for a massive project, but when you arrived at the job site, half the materials were just gone. This is the missing baryon problem, and it's a huge embarrassment for astronomy because it means we've lost track of an enormous amount of the universe's normal content. So where could half of all the atoms in the universe possibly be hiding? The leading suspect is a vast, diffuse web of incredibly hot gas that stretches between galaxies, known as the warm-hot intergalactic medium, or WIM. This isn't the cold, dense gas we find inside galaxies. This is gas that has been heated to temperatures between 100,000 and 10 million degrees Kelvin by the immense shock waves generated by the formation of the largest structures in the universe. As great walls and filaments of galaxies formed under the pull of gravity, the material falling into these cosmic scaffolds would have collided and been heated to extreme temperatures. This gas is so hot that it doesn't glow in visible light. It's essentially invisible to optical telescopes, and it's so thin, so incredibly diffuse that a cubic meter of this space might contain only a few particles of gas, a vacuum far emptier than anything we can create in our best laboratories on Earth. Trying to detect it is like trying to see a faint, hot mist from thousands of miles away. We know it must be there, this cosmic cobweb of matter, because our models of structure formation demand it, but proving its existence and measuring its mass has been one of observational astronomy's toughest challenges. The hunt for this missing matter has required incredible ingenuity and some of the most powerful telescopes ever built, but they aren't looking for the gas itself. Instead, astronomers use it as a sort of cosmic fog. The technique involves looking at the extremely bright, steady light from distant objects called quasars, which are the blazing cores of active galaxies powered by voracious supermassive black holes. As this intense light travels across the universe on its way to us, it passes through these vast filaments of the WIM. The hot gas in these filaments absorbs very specific wavelengths of the quasar's light, imprinting faint fingerprints on the spectrum. It's like analyzing a brilliant light that has passed through a faint, hot fog. By studying the specific colors of light that are missing, scientists can deduce the composition, temperature, and density of the fog it traveled through. This has yielded some promising results, with several teams claiming to have detected the absorption signatures of highly ionized oxygen atoms in the WIM, finally finding clues to the whereabouts of the missing baryons. Yet the case is not yet closed. These detections are incredibly difficult to make, and the signals are tantalizingly faint. While the evidence is mounting that the WIM is indeed the repository for the universe's lost atoms, we still lack a complete census. We haven't mapped this cosmic web in its entirety, and it's possible that some of the missing matter could be hiding in other forms, perhaps in even hotter gas that doesn't betray its presence through these absorption lines. The search continues, a meticulous piece of cosmic detective work that aims to account for every last atom, to complete the inventory of the normal universe and finally solve the mystery of matter that was lost, but now appears to have been hiding in plain sight all along, woven into the very fabric of the cosmos itself. But the grand structures of the cosmos and the hidden matter between galaxies are not the only wanderers in the dark. Imagine a world untethered, a planet with no sun. It drifts through the interstellar void in perpetual night, a frozen orb without a sunrise, without a season, its only light the distant, cold gleam of the Milky Way. This is not science fiction, it is a rogue planet, and these solitary nomads are one of the most intriguing and mysterious populations in our galaxy. For centuries, we assumed planets were, by definition, satellites, forever bound to their parent stars. The discovery of these free-floating worlds shattered that assumption, revealing a universe where planets can be flung from their cradles or even born in the darkest, coldest regions of space entirely on their own. The existence of these lonely worlds was first seriously proposed in the late 1990s, as our techniques for finding exoplanets were just taking off. The primary methods for planet hunting at the time, like the transit method, which looks for a star dimming as a planet passes in front of it, or the radial velocity method, which detects a star's wobble, were designed to find planets tightly bound to their stars. They were blind to planets adrift in the emptiness between them. The breakthrough came with a clever application of a phenomenon predicted by Einstein's theory of general relativity, gravitational microlensing. This occurs when a massive object, like a planet or a star, passes directly between Earth and a distant background star. The rogue planet's gravity acts like a tiny lens, bending and focusing the light from the background star, causing it to temporarily brighten in a very specific, recognizable way. It's a fleeting event, a flash in the cosmic dark that might last only hours or days, but it provides a powerful tool for sensors taking in the darkest parts of the galaxy. Through meticulous microlensing surveys, astronomers have estimated these rogue planets are astonishingly common, with numbers potentially reaching into the hundreds of billions in the Milky Way alone, possibly outnumbering stars themselves. This staggering abundance immediately raises a fundamental question of origins. How did these planets become untethered? There are two compelling and dramatic narratives. The first is a story of cosmic ejection, a violent birthright. In the chaotic early days of a young solar system, planetary orbits are unstable. Giant planets form and begin to jostle for position, their immense gravitational pulls tugging at one another. In this gravitational tug-of-war, a smaller planet can easily become a pawn, slingshotted outward by the gravity of a larger sibling. If it gains enough velocity, it can achieve escape velocity, breaking free of its star's gravitational pull entirely and being thrown out into the galactic wilderness, destined to wander forever. Our own solar system may have ejected its own share of such worlds billions of years ago during its turbulent youth. The second, even more fascinating origin story suggests that some rogue planets were never bound to a star at all. In the cold, dense cores of interstellar gas clouds, regions of material could collapse under their own gravity. However, if the clump of material is too small to ignite fusion and become a star, it might instead form a planet-mass object directly from the nebula, a solitary world born in isolation. These objects, sometimes called sub-brown dwarfs, would be true orphans from the very beginning, never knowing the warmth of a stellar parent. The implications for potential life on such a world are as dark and cold as the planets themselves, yet not without a flicker of possibility. A sunless world would be a profoundly hostile environment. Its surface would be frozen solid, with surface temperatures hovering just a few degrees above absolute zero. Without stellar energy to drive weather systems or photosynthesis, the planet would be a still, silent, and barren wasteland. However, life on Earth has proven to be incredibly resilient, finding ways to thrive in the most extreme environments. The key for a rogue planet would be an internal heat source. If the planet is large enough and still retains heat from its formation, or if it has a radioactive core and active geology like volcanism or tectonic activity, it could maintain a vast subsurface ocean of liquid water beneath a thick shell of ice. We see a version of this on moons in our own solar system, like Europa or Enceladus, which are heated not by the sun but by the gravitational tug of war with their parent planet. A rogue planet with a similar internal furnace could harbor a deep, dark subglacial sea, potentially providing a stable environment for microbial life or even more complex organisms for billions of years, completely isolated from the rest of the galaxy. It is a haunting thought that the most common abodes for life in the universe might not be Earth-like worlds orbiting sunny stars, but frozen, dark nomads adrift and alone in the endless night. But our planet holds a mystery of its own, one that reaches back to the very dawn of our world and challenges our understanding of its most fundamental relationship, the warmth of the sun. Cast your mind back 4 billion years to an Earth that is both alien and familiar. The continents are barren, volcanic activity is rampant, and the first simple life is just beginning to stir in the oceans. According to our most robust models of stellar evolution, the sun burning in that primordial sky should have been significantly dimmer, about 25 to 30% less luminous than it is today. A star's brightness increases gradually over its lifetime as hydrogen in its core is converted to helium, increasing the density and temperature where fusion occurs. This presents a seemingly insurmountable physics problem. With a fainter young sun, the Earth should have been a frozen, ice-locked snowball from pole to pole for its first 2 billion years. The energy output simply wouldn't have been enough to keep the oceans liquid, and yet the geological record tells a completely different and utterly contradictory story. Ancient rocks from that era, known as the Archean, show clear and unambiguous evidence of flowing water, sedimentary deposits, and even the earliest forms of life. These features are impossible to form on a globally glaciated planet. This glaring contradiction between astrophysical theory and geological fact is known as the faint young sun paradox, and it has been one of the most persistent and fascinating puzzles in planetary science. The search for a solution forces us to look inward to the blanket of air that surrounds our planet. The most compelling answer is that the early Earth's atmosphere was a far more effective insulator than it is today, creating a powerful greenhouse effect that trapped the sun's meager heat with incredible efficiency. The leading candidate for this super greenhouse gas is carbon dioxide. Our planet was a vastly more volcanic place in its youth, and these eruptions would have pumped colossal amounts of CO2 into the atmosphere. If the concentration was high enough, it could theoretically have provided the necessary warming. However, when scientists run the models, they find that CO2 alone might not be enough. To achieve the required temperatures, atmospheric CO2 levels would need to have been impossibly high, perhaps hundreds of times greater than today. There's a problem with that scenario too. Geological evidence from ancient soils and isotopes suggests that while CO2 was higher, it wasn't nearly that extreme. This indicates that other, more potent greenhouse gases must have been part of the atmospheric mix, working in concert with carbon dioxide to keep the planet snug. The most likely partner in this climatic balancing act is methane. Produced by early methanogenic microbes, methane is a greenhouse gas dozens of times more effective at trapping heat than CO2. An atmosphere rich in both CO2 and methane could have easily provided the extra warmth needed, creating a cozy, if somewhat toxic, environment for life to emerge. This leads to a beautiful and self-reinforcing hypothesis. Life itself may have been the solution to the paradox. The very first organisms thriving in the warm seas could have been actively maintaining the conditions necessary for their own survival by releasing methane, effectively acting as a planetary thermostat. But this solution introduces a new puzzle of its own. Methane is unstable in an atmosphere that contains oxygen. It quickly breaks down. The early Earth's atmosphere had virtually no free oxygen, making it a perfect environment for methane to accumulate. However, around 2.4 billion years ago, this delicate balance was shattered by the Great Oxidation Event, when cyanobacteria began pumping oxygen into the air as a waste product. This would have rapidly destroyed the methane greenhouse, plunging the planet into its first, and perhaps most severe, ice age, a snowball Earth event. This suggests the paradox may not have one single solution, but a series of solutions that changed over billions of years as life reshaped its own planet. Other intriguing theories look beyond greenhouse gases altogether. Some propose that the early Earth had a much darker surface with less reflective landmasses and oceans, allowing it to absorb a greater percentage of the Sun's faint light instead of bouncing it back into space. Others have speculated about a temporary and now vanished atmospheric component, like a haze of organic particles or even a different atmospheric pressure that would change the entire thermal dynamics of the planet. There's even the far-out idea that the young sun wasn't quite as faint as we think, perhaps possessing a stronger solar wind that interacted with Earth's magnetic field to create warming effects in the upper atmosphere. The faint young sun paradox remains a vibrant area of research because it sits at the crossroads of astronomy, geology, and biology. It forces us to see Earth not as a static stage for life, but as a dynamic, interconnected system where the rocks, the air, and living organisms are in constant conversation, working together to write a history far more complex and wondrous than we could ever have imagined. While we often picture galaxies as serene, isolated islands of stars, the truth is far more violent and dynamic. Our own Milky Way, a grand spiral that appears so stable from our vantage point, has a dramatic history written in the motions of its stars, a history of a colossal cosmic crash. The evidence for this ancient catastrophe comes not from a visible scar, but from the peculiar behavior of millions of stars charted by the European Space Agency's groundbreaking Gaia mission. This spacecraft has been meticulously mapping the positions, distances, and motions of over 1 billion stars in our galaxy, creating an unprecedented three-dimensional atlas of our cosmic neighborhood. As astronomers sifted through this treasure trove of data, they noticed something deeply strange. A specific population of stars, all residing in the Milky Way's halo, the sparse, spherical cloud of stars that envelops the main disk, were not moving randomly. They were all following highly elongated radial orbits, plunging recklessly toward the galactic center, and then soaring back out to the distant halo like bees swarming around a hive. When plotted in a graph of their orbital energy versus vertical angular momentum, the shape formed by these wild trajectories was unmistakable, a long, streaky sausage. This discovery pointed to a single, inescapable conclusion. These stars were not native to the Milky Way. They were the celestial debris, the scattered remains of a smaller dwarf galaxy that ventured too close to our own billions of years ago. In a violent act of galactic cannibalism, the far more massive Milky Way's immense gravitational tides ripped this intruder apart, shredding its structure and assimilating its stars, but not before the victim's unique orbital signature was permanently imprinted on its captured population. The galaxy responsible for creating this stellar sausage has been named the Gaia Enceladus galaxy, though the vivid descriptor Gaia sausage has stuck in the popular imagination, a fitting name for this scrambled cosmic remnant. By studying the metallicity, the abundance of elements heavier than hydrogen and helium in these sausage stars, astronomers could peer even further back in time. These stars were notably metal-poor compared to the Milky Way's native stars at the time, indicating the Gaia sausage galaxy was a relatively primitive entity, having not hosted the generations of star formation needed to enrich its gas with heavy elements. This ancient merger was no minor fender bender. It was a defining event that fundamentally reshaped our galaxy. The timing of this collision, estimated to have occurred between 8 and 11 billion years ago, aligns with a critical period of the Milky Way's adolescence. The impact is believed to have dramatically puffed up the proto-Milky Way's disk, contributing significantly to the formation of the thick disk component we observe today, a region populated with older stars that orbit above and below the main galactic plane. It may have even triggered a massive burst of star formation and funneled material toward the central supermassive black hole, feeding it and influencing the growth of the galactic bulge. This single event paints a picture of a galaxy's growth that is far from peaceful. It is a story of accumulation through violent acquisition, a celestial survival of the fittest where larger galaxies grow by consuming their smaller neighbors. This discovery naturally leads us to wonder just how common such events are. Is our galactic history unique, or is it the universal rule? Observations of other galaxies, like the spectacular antennae galaxies locked in a destructive dance, show that galactic cannibalism is a widespread phenomenon. The Milky Way is currently in the process of digesting several smaller dwarf galaxies, like the Sagittarius dwarf spheroidal, and is on a collision course with the Andromeda galaxy, set to merge in about 4 billion years. The saga of the Gaia sausage reveals that our home galaxy is a composite entity, a cosmic museum holding the fossilized remains of its past conquests, and it challenges us to see the apparently stable night sky for what it truly is, a snapshot in an endless, dynamic, and often violent dance of creation and destruction. From the galactic collisions that shape our home to the quantum realm that underpins all of reality, we now venture into one of the most bizarre and mind-bending concepts in all of physics, a phenomenon so strange that even Albert Einstein himself famously rejected it, calling it spooky action at a distance. We're talking about quantum entanglement, a peculiar connection between particles that seems to defy our everyday understanding of space and time. At its heart, entanglement is a simple idea with staggering implications. Imagine you have a pair of particles, like two electrons, that are born from the same event or interact in a specific way. According to the rules of quantum mechanics, these particles become linked or entangled. Their properties, such as their spin or polarization, are not defined independently but are instead part of a shared, unified quantum state. It's as if you had a pair of magical dice that are forever linked. No matter how far apart you roll them, if one lands on 6, the other will instantly show a 1 or some other perfectly correlated outcome. The truly astonishing part is that this connection appears to be instantaneous. If you measure the property of one entangled particle here on Earth, you instantly know the corresponding property of its partner, even if that partner is on the other side of the galaxy. This spookiness that troubled Einstein comes from the apparent violation of a fundamental principle in physics, that no information can travel faster than the speed of light. According to his theory of relativity, light speed is the ultimate cosmic speed limit. Yet, entanglement seems to suggest a connection that operates outside of that constraint, a ghostly link that transcends the vast distances of space. For decades, this was a philosophical debate, but then, in the 1960s, physicist John Stuart Bell devised a theoretical test, now known as Bell's theorem, which provided a way to experimentally distinguish between Einstein's worldview, which demanded local realism, meaning objects are only influenced by their immediate surroundings, and the stranger quantum view. When scientists finally performed these experiments, the results were clear and unequivocal. The quantum world won. Entanglement is real. The particles really are connected in a way that cannot be explained by any local hidden variables. This has been confirmed repeatedly, with entangled particles separated by hundreds of kilometers in experiments using fiber optic cables and even via satellites, demonstrating that this bizarre connection persists across astonishing distances. But how does this actually work? What is the mechanism? The frustrating yet thrilling answer from quantum mechanics is that there is no mechanism in the classical sense. There is no tiny wire or wave transmitting a signal. Instead, the two particles are not really two separate entities but parts of a single, indivisible quantum system. The act of measuring one particle doesn't send a signal to the other. It simply defines the state of the entire system at once, regardless of the spatial separation. This forces us to reconsider the very nature of reality. It suggests that at the most fundamental level, the universe is non-local. The properties of things may not be absolute until they are measured, and space itself might not be the empty stage we imagine it to be, but rather an emergent property of a deeper, more interconnected reality. This is where the connection to the fabric of spacetime itself becomes a topic of intense speculation and cutting-edge research. Some physicists like Leonard Susskind and Juan Maldacena have explored the idea of a profound link between entanglement and Einstein's general relativity through concepts like the ER=EPR conjecture. This mind-bending proposal suggests that the strange, non-local connection of entanglement might be geometrically encoded in the fabric of spacetime. In this view, the phenomenon we call quantum entanglement could be the microscopic explanation for the very existence of spacetime, the wormholes that theoretically connect distant points and the force of gravity itself. It's a hypothesis that attempts to bridge the greatest divide in modern physics, the chasm between the quantum world of the very small and the relativistic world of the very large. The potential implications of harnessing entanglement on a cosmic scale are revolutionary. We are already developing technologies based on this principle, such as quantum cryptography, where entangled particles can create theoretically unbreakable codes. If someone tries to eavesdrop on the quantum key, the act of measurement disturbs the entangled state, alerting the users immediately. Looking further ahead, a quantum internet, a network connected by entangled links, could enable unimaginably fast and secure global communication. But the most profound applications might lie in our fundamental understanding of the cosmos. Could entanglement be used to create a new type of telescope? One that uses entangled photons to achieve a resolution far beyond any conventional instrument, perhaps even allowing us to peer into the secrets of black holes or the first moments of the Big Bang. Might it be the key to understanding the holographic principle, the idea that our three-dimensional reality is a projection of information stored on a two-dimensional surface at the universe's boundary? Each of these ideas pushes the boundaries of science fiction, yet they are all active areas of serious theoretical research. Quantum entanglement is no longer just a curious footnote in physics textbooks. It is a fundamental feature of our universe, a cosmic thread connecting the smallest particles to the largest structures, and its full understanding may very well unlock the next great revolution in our comprehension of existence itself. Imagine having two of the most precise and celebrated cosmic yardsticks ever devised, each painstakingly calibrated by generations of brilliant scientists, and then discovering they give you two irreconcilable answers for one of the most fundamental numbers in the universe. This is not a thought experiment, it is the reality facing cosmologists today, a puzzle so significant it has been given a name that evokes a gathering storm, the Hubble tension. At its heart is the Hubble constant, a single number that quantifies the current rate of the universe's expansion. For decades, astronomers have worked to pin down this value with ever greater precision, confident that different methods would eventually converge on a single, universal truth. Instead, they have walked directly into a crisis, a discrepancy that has only grown more stubborn with each new, more accurate measurement, suggesting that our understanding of the cosmos might be missing a crucial piece. The roots of this tension lie in two distinct and seemingly impeccable methods of measurement. The first approach looks back to the universe's infancy, to the cosmic microwave background radiation. This fossilized light, a snapshot of the universe when it was just 380,000 years old, is our most powerful tool for understanding the early cosmos. By mapping the subtle temperature fluctuations in this radiation with exquisite detail, missions like Planck can determine the precise ingredients of the universe, the amounts of ordinary matter, dark matter, and dark energy, and calculate how this mix should have evolved over 13.8 billion years to produce the expansion rate we see today. This is a top-down, model-dependent method. It tells us that based on our best model of cosmology, the Hubble constant should be about 67.4 kilometers per second per megaparsec. This means that for every megaparsec of distance, a length equal to 3.26 million light-years, a galaxy is moving away from us 67.4 kilometers per second faster. The second method takes a bottom-up local approach, building a cosmic distance ladder right here in the modern universe. Astronomers use incredibly reliable stars like Cepheid variables and Type 1a supernova as standard candles. These are objects whose intrinsic brightness is known, allowing scientists to calculate their distance by measuring how dim they appear. By measuring both the distance and the redshift, the stretching of light wavelength due to the expansion of space of these objects in relatively nearby galaxies, they can directly calculate the current expansion rate. Teams led by the likes of Nobel laureate Adam Rees have refined this technique to an astonishing degree, using the Hubble Space Telescope to meticulously observe Cepheid variables in the same galaxies that host supernova, creating a robust and precise cosmic ladder. Their result is unequivocal and consistently higher than the Planck measurement, approximately 73 kilometers per second per megaparsec. The difference might seem small, only about 5.6, but the uncertainty margins on these two world-class measurements no longer overlap. They are fundamentally statistically inconsistent. It is the equivalent of two superior clocks, each claiming to tell the perfect time, yet ticking at an undeniably different pace. This stubborn disagreement has sent cosmologists on a frantic search for explanations, which broadly fall into two camps. The first possibility is the more humbling one, that one or both sets of measurements contain a hidden systematic error, an unaccounted-for flaw in our observations. Perhaps our understanding of the physics of Cepheid variables has a subtle blind spot, or maybe our measurement of distances within our own galactic neighborhood, which forms the first rung of the cosmic ladder, is less certain than we think. On the early universe side, could there be an unconsidered contaminant in the cosmic microwave background data? So far, despite intense scrutiny, no one has found a systematic error large enough to resolve the tension. In fact, as observational techniques have improved, the gap has only become more pronounced, strengthening the case for the second, far more thrilling possibility, that this is not an error but a discovery. The Hubble tension could be our first empirical hint that the standard model of cosmology, the incredibly successful lambda-cold dark matter model, is incomplete. If the discrepancy is real, it forces us to ask what ingredient we might be missing. The most compelling theoretical fixes involve making dark energy, the mysterious force accelerating the expansion, more complex. In the standard model, dark energy is constant, represented by Einstein's cosmological constant. But what if dark energy is not constant? What if its strength has changed over time? Perhaps it was weaker in the early universe and has grown stronger, which could explain why the universe is expanding faster now than our models, based on early universe data, predict. Other theories propose a previously unknown interaction between dark energy and dark matter, or even the existence of a new type of relativistic particle that flooded the early universe and subtly altered its evolution. Some of the most radical ideas suggest that the Hubble tension is a sign that dark matter itself possesses unique properties, allowing it to interact with itself or with light in ways we haven't yet detected. Each of these proposals is a potential doorway to new physics, a clue that the cosmos is even stranger and more wonderful than we have so far dared to imagine. The resolution of the Hubble tension is now one of the most urgent goals in all of astronomy. New observatories like the James Webb Space Telescope are turning their powerful gaze toward the cosmic distance ladder, aiming to measure Cepheid variables and supernova with unprecedented precision to confirm or deny the local measurements. Meanwhile, next-generation experiments are being designed to map the cosmic microwave background with even finer detail. This isn't just a debate over a number, it is a profound test of our cosmic self-awareness. It asks whether we truly understand the narrative of the universe from its first chapter to the present day, or if we have been misreading the story all along. The tension is a thrilling reminder that the universe is the ultimate authority, and it is our job to listen carefully, even when the answers it gives us are not the ones we expected. Far beyond the orbit of Neptune, in the cold, dark reaches of our solar system, lies a vast and mysterious frontier known as the Kuiper Belt. This distant realm is home to a diverse population of icy bodies, remnants from the solar system's earliest days, including the beloved dwarf planet Pluto. For decades, astronomers have mapped this region, expecting its population to gradually thin out the farther one travels from the Sun, much like a cosmic beach where the sand slowly gives way to the ocean. But recent surveys have revealed something deeply puzzling, a boundary so abrupt and unexpected it has been dubbed the Kuiper Cliff. At approximately 50 astronomical units from the Sun, that's 50 times the distance from Earth to the Sun, the number of detected Kuiper Belt objects doesn't gently decline, it plummets. It's as if you were walking along that beach and suddenly, without warning, stepped off the edge of a continental shelf into an abyssal plain. This sharp drop-off presents a direct challenge to our most fundamental models of solar system formation, which predict a much more gradual decrease in object density. The cliff suggests something is actively shepherding this distant frontier, and the most thrilling possibility is that we are feeling the gravitational influence of a world we have yet to lay eyes on. This is where the hunt for Planet 9 enters the story. The idea of a large, unseen planet lurking in the outer darkness is not new. It's how we discovered Neptune itself by tracking its gravitational pull on Uranus. The modern hypothesis for Planet 9 was propelled by a different set of orbital oddities. Astronomers Konstantin Batygin and Mike Brown at Caltech noticed that the most distant Kuiper Belt objects, those with highly elongated orbits that take them hundreds of astronomical units from the Sun, share a peculiar characteristic. Their orbits are clustered together, and their points of closest approach to the Sun, their perihelia, are grouped in a similar direction of space. For this clustering to persist and not be randomized over billions of years by the gravity of the giant planets we know, the models suggest it must be shepherded by the persistent tug of a massive object. Their calculations point to a world with a mass roughly 5 to 10 times that of Earth, on a colossal elliptical orbit that takes it between 300 and 1,000 astronomical units from the Sun. A single orbit for this proposed planet could take an astonishing 10 to 20,000 years. The gravitational influence of such a body could very well be the sculpting force behind the Kuiper Cliff, efficiently ejecting objects from that region or herding them into orbits that keep them away from the cliff's edge, effectively creating a gravitationally carved void. However, the Planet 9 theory, while compelling, is not the only possible explanation for this distant anomaly. Some planetary scientists argue that the cliff might not point to a present-day planet, but could instead be a fossilized relic from the solar system's violent infancy. Our current model of planetary formation, the NICE model, describes a period of dramatic instability among the giant planets shortly after they formed. During this chaotic era, Jupiter, Saturn, Uranus, and Neptune likely migrated from their original orbits, scattering countless icy planetesimals in every direction. This grand reshuffling could have stripped the outer disk of material very early on, depositing it into the scattered disk or ejecting it from the solar system entirely, and leaving behind a sharp edge that has been frozen in time for billions of years. In this scenario, the Kuiper Cliff is not a dynamic feature being maintained today, but a ghostly imprint of a cataclysm that occurred over 4 billion years ago. The orbital clustering of extreme objects could then be explained as a similar fossilized effect, a memory of a past gravitational disturbance rather than an ongoing one. The search for a definitive answer is a monumental technical challenge. Surveying the sky for a faint, slow-moving object at such incredible distances requires the most powerful telescopes and immense patience. Projects like the Vera-C, Rubin Observatory's legacy survey of space and time are poised to revolutionize this search. With its ability to scan the entire visible sky deeply every few nights, it could either finally catch a glimpse of Planet 9's faint glow or, perhaps just as importantly, rule out its existence across vast swaths of its predicted orbital path. Each new discovery of an extreme trans-Neptunian object adds another data point, refining the possible location of the hypothetical planet or further testing the limits of the fossilized relic theory. The Kuiper Cliff stands as a stark reminder that our solar system's story is far from fully written. It represents a boundary not just in space, but in our understanding, a tantalizing puzzle that pushes our observational capabilities to their limit and forces us to consider whether we share our celestial neighborhood with a giant world still waiting to be discovered. From the fleeting, singular enigma of the WOW signal to the grand gravitational puzzle of Planet 9, our journey through these 25 unexplained anomalies reveals a universe that is far stranger, more dynamic, and more beautifully mysterious than we could have ever imagined. Each one of these cosmic riddles, from the ghostly pull of dark matter to the defiant zombie stars that cheat death, serves as a profound reminder that our understanding of the cosmos is not a completed map, but a living, breathing draft, a work in progress constantly being revised by the next great discovery. These aren't mere gaps in our knowledge, they are vibrant frontiers, the very edges of human understanding where science meets wonder and speculation sparks the next generation of exploration. They prove that the universe's greatest gift to us is not just the answers we've found, but the magnificent questions that remain. As we stand here on our pale blue dot, looking out into the infinite dark, these mysteries connect us to the countless generations of stargazers who came before us and to the future explorers who will one day build upon the foundation we're laying today. They are a call to curiosity, an invitation to look up and wonder, to question, and to never stop seeking. The story of the cosmos is still being written, and each of these anomalies is a thrilling, unwritten chapter waiting for its author. So now, we want to hear from you. Which of these celestial puzzles captured your imagination the most? Was it the silent, waiting question of the Fermi Paradox, the impossible geometry of Saturn's hexagon, or the ghostly whisper of the WOW? Signal echoing through decades, share your thoughts and your own favorite cosmic mysteries in the comments below. We read every single one. If this journey through the unknown sparked your curiosity, help us continue exploring by hitting the like button, subscribing to the channel, and ringing that notification bell so you never miss our next deep dive into the universe's greatest secrets. Until next time, keep looking up.